Welcome to our channel, where we explore the mysteries of the universe. Today we're diving into one of the most profound questions in cosmology. How can the universe be infinite? The idea of an infinite universe has fascinated scientists and philosophers for centuries. But what does it really mean for the universe to be infinite? And how can we even begin to comprehend such a vast concept? First, let's define what we mean by infinity. In mathematics, infinity is a concept that describes something without any limit. It's not a number, but rather an idea that represents boundlessness. When applied to the universe, infinity suggests that space extends endlessly in all directions. This means there's no edge, no boundary, and no end to the universe. It's a mind-bending thought, but one that has significant implications for our understanding of reality. Historically, many cultures and civilizations have grappled with the concept of infinity. From ancient Greek philosophers to modern-day scientists, the idea has evolved and transformed over time. One of the key pieces of evidence supporting an infinite universe comes from the Big Bang theory. According to this theory, the universe has been expanding since its inception. If this expansion continues indefinitely, it suggests that the universe could be infinite in size. But how do we reconcile this with our observable universe? The part of the universe we can see is limited by the speed of light and the age of the universe. However, beyond this observable horizon, there could be an endless expanse of space. Cosmological models also play a crucial role in this discussion. Models that describe an open or flat universe suggest that space could be infinite. These models are supported by observations of the cosmic microwave background radiation and the distribution of galaxies. Finally, the concept of infinity isn't just a scientific question. It's also a deeply philosophical one. It challenges our perceptions of reality, our place in the cosmos, and the nature of existence itself. Mathematically, infinity is an abstract concept that represents an unbounded quantity. Unlike finite numbers, infinity is not a specific value but rather an idea that describes something larger than any number we can imagine. In calculus, infinity is often used to describe the behavior of functions as they approach very large or very small values. For instance, the function 1x approaches infinity as x approaches 0. This helps mathematicians understand limits and behaviors of different mathematical models. Set theory, a branch of mathematical logic, explores different sizes or cardinalities of infinity. The most familiar is the infinity of natural numbers, 1, 2, 3, and so on. However, there are larger infinities, such as the infinity of real numbers between 0 and 1. Georg Cantor, a mathematician in the 19th century, made significant contributions to our understanding of different types of infinity. He demonstrated that not all infinities are created equal. Some infinities are actually larger than others. Cantor's work introduced the concept of countable and uncountable infinities. Countable infinity includes things like the set of all integers. Uncountable infinity includes sets like the real numbers, which are so numerous they can't be matched one-to-one with the integers. In geometry, infinity is often visualized in terms of lines extending without end. For example, a line on a graph theoretically continues infinitely in both directions. This helps in understanding concepts like asymptotes and limits. In topology, a branch of mathematics focused on properties preserved under continuous deformations, infinity can describe spaces that have no boundaries. This helps in the study of shapes and spaces that extend infinitely. In algebra, infinite sequences and series are used to describe sums that continue indefinitely. These are crucial in various fields of science and engineering, helping to model real-world phenomena. Infinity also appears in probability theory, where it can describe events with an infinite number of outcomes. For instance, rolling a fair die theoretically has an infinite series of possible results over time, though practical limits constrain it. The concept of infinity is also crucial in fractal geometry, where shapes can have infinite complexity. Fractals show self-similar patterns at every scale, revealing infinite detail within a finite space. Mathematical models of the universe often incorporate infinity to describe its vastness. For example, Einstein's equations of general relativity imply that space can stretch infinitely under certain conditions. In physics, infinity can represent phenomena that go beyond our current understanding. For instance, singularities in black holes are regions where densities approach infinity, challenging existing physical theories. Infinity poses intriguing paradoxes and problems in mathematics. The famous Hilbert's hotel paradox illustrates a hotel with infinitely many rooms that can still accommodate more guests, highlighting the counterintuitive nature of infinity. The study of infinity also intersects with computer science, where algorithms must handle potentially infinite processes. This is especially relevant in fields like artificial intelligence and data analysis. Understanding infinity requires a blend of mathematical rigor and philosophical inquiry. It pushes the boundaries of human comprehension, inviting us to explore beyond the limits of the finite world we know. Infinity is not just a mathematical concept, but a profound philosophical idea. It challenges our understanding of reality and existence. Philosophers have long debated the implications of an infinite universe and what it means for our place within it. One major philosophical question is whether an infinite universe implies an infinite number of possibilities. If the universe is truly infinite, every possible event might occur somewhere. This brings up intriguing notions of parallel realities and the multiverse. The idea of an infinite universe also raises questions about the nature of time. If the universe has no beginning or end, does time itself stretch infinitely backward and forward? This challenges our conventional understanding of time as a linear progression. Another philosophical implication concerns the concept of meaning. In an infinite universe, the idea of a unique, purposeful existence is complicated. Does an infinite cosmos diminish the significance of individual lives? Or does it enhance the wonder of our existence? Infinity also touches on the question of determinism versus free will. In an infinite universe, are our actions predetermined by an infinite chain of events, or do we have true agency? This debate has profound implications for ethics and morality. The infinite nature of the universe can lead to existential questions about our purpose. If the cosmos is boundless and we are just a tiny part of it, what is our role? This contemplation can be both humbling and awe-inspiring. Philosophers also ponder the relationship between infinity and God. An infinite universe might suggest an infinite creator, or it might imply that the universe itself is eternal and self-sustaining. These questions bridge the gap between science and theology. The concept of infinity can also influence our understanding of consciousness. If the universe is infinite, is consciousness a unique feature of our minds? Or is it a universal phenomenon that could arise elsewhere in the cosmos? The infinite universe theory challenges our perception of space. If space is truly boundless, then our understanding of location and distance needs to be re-evaluated. This can alter how we perceive our immediate environment and our place in the cosmos. Infinity in the universe brings up the question of the observable versus the unobservable. If the universe is infinite, most of it lies beyond our observational reach. This challenges our scientific methods and the limits of human knowledge. An infinite universe also affects how we think about the future. If time and space are unbounded, the future holds limitless possibilities. This can be a source of hope and imagination, but also of uncertainty and unpredictability. Philosophically, the infinite universe can lead to discussions about the nature of existence itself. What does it mean to exist in an infinite cosmos? This question touches on fundamental aspects of identity and being. The idea of an infinite universe can inspire awe and wonder. The sheer scale and complexity of an endless cosmos can evoke a sense of the sublime, where human understanding meets the vastness of the unknown. Infinity in the universe also encourages a deeper appreciation for the here and now. In the face of boundlessness, the finite moments we experience gain a unique significance, making our everyday lives more precious. Ultimately, the philosophical implications of an infinite universe invite us to explore the limits of human thought. They challenge us to expand our understanding, question our assumptions, and embrace the mysteries of the cosmos. When we look at nature, we find examples that hint at the concept of infinity. Take the horizon, for instance. No matter how far you travel, it always seems to recede, never quite reachable. Consider the night sky. On a clear night, the sheer number of stars seems endless. Each star is a distant sun, and beyond them are even more galaxies, suggesting an infinite expanse of space. The ocean is another powerful metaphor for infinity. Standing on the shore, watching the waves stretch out to the horizon, gives a sense of boundless water. The depths of the ocean, much like the cosmos, seem to have no end. Fractals are a mathematical phenomenon found in nature. A snowflake, for instance, displays intricate patterns that repeat at every scale. This self-similarity, where a structure looks similar no matter how closely you zoom in, evokes the idea of infinity. Tree branches and roots also exhibit fractal patterns. Each branch splits into smaller branches, and those into even smaller ones, potentially infinitely. This recursive nature illustrates how complex patterns can emerge from simple rules. Rivers and their tributaries create another fractal-like structure. A river system, with its main river splitting into countless smaller streams, mirrors the concept of infinite division and complexity in nature. Cloud formations often display fractal characteristics. The intricate patterns seen in clouds can repeat at different scales, suggesting a form of infinite complexity in the atmosphere. The human vascular system is an example within our own bodies. Our veins and arteries branch out extensively, creating a network that ensures blood reaches every cell. This branching resembles an infinite pattern, essential for sustaining life. Similarly, the structure of our lungs involves repeated branching. The bronchial tubes divide into smaller airways, ensuring efficient gas exchange. This repeated division is crucial for breathing and mirrors the concept of fractals. The coastline paradox highlights another natural example of infinity. The length of a coastline can appear infinite depending on the measurement scale used. The closer you look, the more detail you see, making the length seem unending. Sand dunes present a desert landscape that stretches endlessly. The repeating patterns of dunes create a sense of infinity, as the landscape seems to go on without end in every direction. Coral reefs exhibit complex branching structures. These underwater ecosystems are vast and intricate, with patterns that can seem infinitely detailed, supporting a wide array of marine life. Mountains and their ranges often give the impression of infinity. When viewed from a distance, the repeating peaks and valleys appear to extend indefinitely, creating a majestic, endless panorama. Even in microscopic scales, infinity appears. The arrangement of atoms in a crystal lattice, for instance, repeats in a pattern that can theoretically extend forever, showcasing an ordered form of infinity. Lastly, the rings of Saturn provide a celestial example. The countless particles and ice chunks that make up the rings orbit the planet in a seemingly infinite array, creating a striking visual representation of boundless beauty in our solar system. Infinity extends beyond just space, playing a crucial role in our understanding of time. Time, like space, can be perceived as having no beginning and no end, stretching infinitely in both directions. Consider the concept of eternity in various cultures and religions. Eternity represents an infinite duration, a timeless existence that transcends the finite lifespan of humans and even the universe itself. In physics, time dilation shows how time can stretch infinitely under certain conditions. As objects approach the speed of light, time for them slows down, theoretically extending to infinity. The arrow of time, representing the flow from past to future, suggests a one-way journey through an infinite timeline. This linear progression implies that time, like a river, flows endlessly forward. Philosophically, the idea of eternal recurrence proposes that time is cyclical. According to this concept, every event will eventually repeat infinitely, creating a loop that has no beginning or end. In literature and art, infinity is often depicted through themes of timeless love, eternal quests, and endless adventures. These narratives explore the human fascination with an unending timeline and our place within it. The infinite regress argument in philosophy challenges the idea of a definitive starting point. It questions what caused the first event and what caused that cause, leading to an infinite chain of reasoning. In cosmology, the concept of the multiverse suggests infinite parallel universes, each with its own timeline. This theory extends infinity to the very fabric of reality, proposing countless alternate histories and futures. Theoretical physics introduces the idea of infinite dimensions. Beyond our familiar 3 dimensions of space and 1 of time, there could be additional dimensions that extend infinitely, fundamentally altering our perception of reality. Time travel narratives often delve into infinity. The idea of traveling back and forth in time, creating infinite loops or parallel timelines, fascinates and challenges our understanding of causality and existence. In mathematics, infinite sequences and series are crucial for understanding patterns and behaviors over time. These concepts help us model phenomena that extend indefinitely, from population growth to economic trends. The concept of infinite lifespans challenges our understanding of human experience. Immortality, whether through biological means or technological advancements, poses profound ethical and existential questions. In geology, the concept of deep time reveals the Earth's history as an almost infinite span. The processes shaping our planet occur over millions and billions of years, far beyond human scales of time. The infinite monkey theorem illustrates infinity in probability. It states that a monkey hitting keys at random on a typewriter for an infinite amount of time will eventually type any given text, such as the complete works of Shakespeare.
In computer science, algorithms that run indefinitely explore the concept of infinity in computation. These algorithms, whether in simulation or data analysis, push the boundaries of what can be processed over limitless time.
Ultimately, the exploration of infinity in various contexts expands our understanding and challenges our perceptions, inviting us to rethink the very nature of existence and our place within the infinite tapestry of time and space. Many people misunderstand the concept of infinity, often confusing it with large numbers. Infinity is not a number, but an idea that represents something without any limit. A common misconception is that infinity means something is bigger than everything else. In reality, infinity isn't a comparative measure, but a way to describe boundlessness. Some believe that infinity can be reached. However, by definition, infinity is unattainable. No matter how far you go or how much you add, you'll never reach infinity. People often think of infinity as a static concept. In fact, infinity can be dynamic, such as an endless process or a never-ending sequence. There's a misconception that all infinities are equal. In mathematics, there are different sizes of infinity. For example, the infinity of real numbers is larger than the infinity of natural numbers. Another misunderstanding is that infinity only applies to space. Infinity also applies to time, sequences, and other abstract concepts. Many assume that infinite means everything is possible. While infinity allows for endless possibilities, it doesn't guarantee that every conceivable event will happen. Some think infinity makes things meaningless. On the contrary, infinity can add depth and complexity to our understanding of the universe. A common mistake is to think that infinite sets behave like finite sets. Infinite sets have unique properties that can seem counterintuitive, such as being able to have a subset of the same size as the original set. There's a belief that infinity implies chaos. In reality, infinity can exist within ordered systems, such as mathematical sets or physical theories. People often confuse infinite divisibility with actual physical division. While something can be conceptually divided infinitely, in the physical world, there are limits to division. Infinity in geometry can be misunderstood. For instance, people might think that an infinitely long line means there is no space between points, but in fact there is still a well-defined distance. Some believe that the concept of infinity is purely theoretical and has no real-world applications. Infinity is actually a crucial part of many scientific and engineering disciplines. The idea that infinity is an abstract concept with no visual representation is another misconception. Fractals, for instance, visually represent infinite complexity. Finally, there's the notion that infinity is an easy concept to grasp. In reality, infinity is complex and often requires deep mathematical and philosophical contemplation to understand fully. The theory of an infinite universe stems from the observation that space appears boundless. Scientists propose that the universe has no edges and stretches out endlessly. To understand this, we start with the Big Bang theory, which suggests that the universe has been expanding since its inception. This expansion implies that space itself is growing, potentially without limit. Einstein's theory of general relativity plays a crucial role here. It describes how space and time are intertwined, and how massive objects curve this space-time fabric, influencing the universe's shape and extent. Cosmologists use these principles to create models of the universe. Some of these models predict an infinite universe based on current observations and mathematical equations. One such model is the flat universe model. It suggests that the universe is geometrically flat and will expand forever, making it infinite in extent. The concept of an open universe also supports infinity. An open universe has a saddle-shaped geometry, leading to endless expansion and suggesting infinite space. Evidence from the cosmic microwave background radiation supports these models. This radiation, a remnant of the Big Bang, helps scientists measure the universe's shape and size. Dark energy, a mysterious force driving the accelerated expansion of the universe, further supports the idea of an infinite universe. As dark energy continues to push the universe apart, it hints at infinite growth. Observations of distant galaxies show that they are moving away from us, indicating that the universe is expanding. The further we look, the more galaxies we see, reinforcing the idea of boundless space. Inflation theory, which describes a rapid expansion of the universe just after the Big Bang, also suggests infinity. This brief period of exponential growth could have stretched the universe to an infinite size. Mathematical models of the universe often incorporate infinity to describe its vastness. These models use complex equations to predict how the universe behaves on large scales. Quantum mechanics, while primarily dealing with the very small, also offers insights into infinity. Some interpretations suggest that infinite possibilities exist within quantum systems, aligning with the idea of an infinite universe. The multiverse theory proposes that our universe is just one of many. If true, this could mean that infinite universes exist, each with its own laws of physics and outcomes. String theory, which aims to unify all fundamental forces, introduces the concept of multiple dimensions. These extra dimensions could be infinite, adding another layer to the idea of an infinite cosmos. Ultimately, the theory of an infinite universe challenges and expands our understanding of reality, pushing the boundaries of science and inviting us to explore the limitless possibilities of the cosmos. Evidence supporting the Big Bang theory is extensive and compelling. One of the most significant pieces is the observation of the cosmic microwave background radiation. This faint glow permeates the entire universe, a remnant from the early stages of the cosmos, providing a snapshot of the universe when it was just 380,000 years old. The abundance of light elements such as hydrogen, helium, and lithium is another crucial piece of evidence. The Big Bang theory predicts their formation during the first few minutes of the universe. Observations show that the proportions of these elements in the universe align precisely with the predictions. Hubble's law is fundamental to supporting the Big Bang. Edwin Hubble discovered that galaxies are moving away from us, with their speed proportional to their distance. This observation suggests that the universe is expanding, a key prediction of the Big Bang theory. The large-scale structure of the universe also supports the Big Bang. The distribution of galaxies and clusters of galaxies across vast cosmic scales can be explained by the gravitational collapse of matter from small initial density fluctuations in the early universe, predicted by the theory. The discovery of the cosmic microwave background radiation by Arno Penzias and Robert Wilson in 1965 was a milestone. This radiation provides a thermal imprint of the early universe, matching the theoretical predictions of the Big Bang model. Galactic redshifts provide further evidence. The light from distant galaxies is redshifted, meaning it has been stretched to longer wavelengths due to the expansion of the universe. This redshift is a direct consequence of an expanding universe originating from a hot, dense state. Observations of the oldest stars give us another piece of the puzzle. The ages of the oldest known stars are consistent with the time elapsed since the Big Bang, estimated to be around 13.8 billion years. Gravitational waves also offer support. The detection of these ripples in space-time, particularly those from the early universe, can provide insights into the conditions just fractions of a second after the Big Bang, supporting the theory's predictions. Studies of the cosmic background radiation's slight anisotropies, or temperature variations, reveal information about the universe's early conditions. These tiny fluctuations have been mapped in great detail by satellites like COBE, WMAP, and Planck, providing strong evidence for the Big Bang. The isotropy of the cosmic microwave background radiation is another key piece of evidence. Despite the vastness of the universe, the radiation is remarkably uniform in all directions, supporting the idea that the universe began in a hot, dense state and expanded rapidly. The ratio of dark matter to visible matter observed in the universe aligns with predictions from the Big Bang. This ratio helps explain the formation and distribution of galaxies and clusters, further corroborating the theory. Supernovae observations, particularly those of type Ia supernovae, provide evidence for the accelerated expansion of the universe. This acceleration, driven by dark energy, fits within the framework of the Big Bang and the subsequent evolution of the cosmos. The discovery of primordial gas clouds also supports the theory. These clouds, observed in the distant universe, contain the same proportions of light elements predicted to form in the Big Bang nucleosynthesis, offering a glimpse into the universe's early chemical composition. The theory also predicts the existence of a primordial neutrino background, similar to the cosmic microwave background but composed of neutrinos. Although direct detection is challenging, its predicted effects align with observed phenomena. Together, these pieces of evidence create a cohesive and compelling picture supporting the Big Bang theory, shaping our understanding of the universe's origins and its ongoing evolution. The idea of an infinite universe brings profound implications for our understanding of existence. If the universe is infinite, it suggests that there is no edge, no center, and no boundary to space itself. An infinite universe implies that there could be an infinite number of stars, planets, and possibly even civilizations. This raises the intriguing possibility of other life forms existing somewhere out there, in the vastness of space. With infinity, the concept of repetition becomes a topic of interest. In an infinite universe, every possible arrangement of matter could occur somewhere, meaning that there might be other planets identical to Earth, or even other versions of you. The concept of an infinite universe challenges our understanding of time as well. If the universe has always existed and will always exist, our current era is just a tiny moment in an endless continuum. An infinite universe also impacts our view of cosmology. Traditional models that focus on a finite cosmos need to be adjusted to account for the limitless expanse of space. The laws of physics as we know them might behave differently in different parts of an infinite universe. This variation could lead to regions with entirely different physical constants and laws. Infinity brings about the concept of eternal return, where every possible state of the universe could recur an infinite number of times. This idea has deep philosophical implications about the nature of existence and time. The infinite nature of the universe also raises questions about entropy and the second law of thermodynamics. In an infinite universe, entropy might never reach a maximum, leading to ongoing creation and destruction cycles. Dark matter and dark energy become even more mysterious in the context of an infinite universe. Understanding their roles could reveal new aspects of the cosmos and how it continues to expand indefinitely. Infinity challenges our notions of distance and travel. With no boundaries, the idea of reaching any specific point in the universe becomes even more complex, involving potentially endless journeys. In an infinite universe, the multiverse theory gains traction. If space is limitless, then the existence of multiple, possibly infinite universes becomes a more plausible scenario. The scale of infinity can also affect our understanding of quantum mechanics. Infinite possibilities at the quantum level might lead to new interpretations of particle behavior and fundamental forces. Philosophically, an infinite universe impacts our sense of purpose and significance. If the cosmos is boundless, the human experience might seem both more precious and more fleeting within this grand expanse. In practical terms, an infinite universe poses challenges for scientific exploration. Our observational capabilities are limited, making it difficult to grasp the full extent of an endless cosmos. Finally, the concept of an infinite universe invites us to expand our imaginations and rethink our place in the grand scheme of things, pushing the boundaries of science, philosophy, and human understanding. Several alternatives to the Big Bang theory have been proposed over the years, each offering a different perspective on the universe's origins. One prominent alternative is the steady-state theory, which suggests that the universe has always existed in a constant state without beginning or end. In the steady-state theory, New matter is continuously created as the universe expands, maintaining a constant density. This idea contrasts sharply with the Big Bang's concept of a singular beginning. Another alternative is the oscillating universe theory. This proposes that the universe undergoes endless cycles of expansion and contraction, each beginning with a Big Bang and ending in a Big Crunch, followed by a new Big Bang. The ekpyrotic model offers a different take, suggesting that the universe results from a collision between two three-dimensional worlds on a hidden fourth dimension. This collision generates the hot, dense state we associate with the Big Bang. The plasma cosmology theory emphasizes the role of electromagnetic forces and plasma in the formation and evolution of the universe, downplaying the importance of gravity and offering an alternative to the Big Bang's explanation of cosmic structures. Modified Newtonian dynamics, or MOND, challenges the dark matter hypothesis and offers a different approach to understanding the universe's large-scale structure and expansion, providing an alternative framework to the Big Bang. Quantum loop cosmology proposes that the universe's initial singularity is replaced by a quantum bounce, suggesting a pre-existing contracting phase that led to the current expansion, thus avoiding the concept of a singular beginning. The inflationary universe theory, while often considered an extension of the Big Bang, offers a different perspective by suggesting a rapid exponential expansion shortly after the Big Bang, addressing some of the original theory's limitations. The holographic principle posits that the entire universe can be seen as a two-dimensional information structure projected onto a three-dimensional space, offering a radically different view of the universe's origin and nature.
The cyclic model builds on the concept of an oscillating universe, suggesting that each cycle of expansion and contraction is driven by dark energy, leading to repeated Big Bang-like events without a true beginning or end.
The variable speed of light theory suggests that the speed of light may have been different in the early universe, providing an alternative explanation for cosmic inflation and the observed uniformity of the cosmic microwave background radiation. The black hole cosmology hypothesis proposes that our universe might exist inside a black hole within a larger parent universe, offering a unique perspective on the relationship between black holes and cosmic origins. The anthropic principle argues that the universe's fundamental constants are finely tuned to allow for the existence of life, suggesting that the universe's properties are not random but necessary for our existence, providing a philosophical alternative to the Big Bang. The multiverse theory posits the existence of many universes, each with different physical constants and laws, implying that our universe is just one of countless others, potentially avoiding the need for a singular beginning. Finally, the Big Rip theory suggests that the universe's expansion will eventually tear all matter apart, leading to a future where space, time, and matter cease to exist, offering a dramatic alternative to the Big Bang's eventual fate. The current scientific consensus supports the Big Bang theory as the most comprehensive explanation for the origin and evolution of the universe. This consensus is built on a foundation of extensive observational evidence and theoretical models. Scientists agree that the universe began approximately 13.8 billion years ago from an extremely hot and dense state. This initial singularity expanded rapidly in a process known as the Big Bang. The discovery of the cosmic microwave background radiation provided strong support for the Big Bang theory. This radiation is considered a remnant of the early universe, offering a snapshot of its infancy. Another key piece of evidence is the observed redshift of distant galaxies. Edwin Hubble's observations showed that galaxies are moving away from us, indicating that the universe is expanding, a crucial prediction of the Big Bang. The relative abundance of light elements such as hydrogen and helium aligns with predictions from Big Bang nucleosynthesis. These elements were formed during the first few minutes after the Big Bang, matching observed abundances. The large-scale structure of the universe, including the distribution of galaxies and cosmic voids, fits the patterns predicted by the Big Bang model. These structures formed from small density fluctuations in the early universe. The theory of cosmic inflation, which posits a rapid exponential expansion of the universe shortly after the Big Bang, has gained wide acceptance. It explains the uniformity of the cosmic microwave background and the large-scale structure of the universe. Dark matter and dark energy are integral to the current cosmological model. Dark matter explains the gravitational effects observed in galaxies and clusters, while dark energy accounts for the accelerated expansion of the universe. Observations of type Ia supernovae have provided evidence for dark energy. These supernovae act as standard candles, allowing astronomers to measure cosmic distances and confirm the universe's accelerated expansion. The Planck satellite's detailed measurements of the cosmic microwave background have refined our understanding of the universe's age, composition, and geometry, further supporting the Big Bang theory. Current models suggest that the universe is flat with a slight curvature, consistent with inflationary predictions. This geometric shape influences the ultimate fate of the universe. The consensus also acknowledges that while the Big Bang theory explains much, there are still open questions. The nature of dark matter and dark energy, the conditions before the Big Bang, and the unification of general relativity with quantum mechanics remain areas of active research. Quantum cosmology is a growing field that seeks to understand the universe's origin using principles of quantum mechanics. Theories such as loop quantum gravity and string theory are being explored for their potential to explain the initial singularity. Despite these uncertainties, the Big Bang theory remains the cornerstone of modern cosmology. It provides a coherent and testable framework for understanding the universe's history and evolution. The scientific community continues to refine this model through observations, experiments, and theoretical developments, maintaining the Big Bang as the best explanation for the origin of the cosmos. The observable universe refers to the portion of the entire universe that we can see or detect from Earth. It's defined by the distance that light has traveled since the beginning of the universe, approximately 13.8 billion years ago.
Because the universe has been expanding, the actual size of the observable universe is much larger than 13.8 billion light-years. Current estimates put its diameter at about 93 billion light-years.
The boundary of the observable universe is known as the cosmic light horizon. This is the maximum distance from which light emitted since the Big Bang could have traveled to us. The observable universe includes all the galaxies, stars, and other celestial objects we can see, as well as the cosmic microwave background radiation, which is the afterglow of the Big Bang. Beyond the observable universe, there may be many more galaxies and stars that we cannot see because their light hasn't had enough time to reach us. Our position in the universe is not special. The observable universe is centered around us simply because it's the region from which light has had time to travel to us. The concept of the observable universe is crucial for cosmology because it sets the limits of what we can study and understand about the cosmos. Telescopes and other instruments allow us to observe the distant edges of the observable universe, giving us a glimpse into the past, as we see objects as they were billions of years ago. The observable universe contains an estimated 100 billion galaxies, each with millions or billions of stars, making it incredibly vast and rich with cosmic phenomena. Despite its vastness, the observable universe is just a small part of the entire universe. The total size of the universe could be infinitely larger than what we can observe. The cosmic microwave background radiation provides a critical map of the observable universe, showing temperature fluctuations that correspond to density variations in the early universe. Understanding the observable universe helps scientists infer the properties and behavior of the entire universe, even though they can't observe it all directly. Redshift measurements of distant galaxies help determine how fast the universe is expanding, giving insight into the scale and structure of the observable universe. Dark energy and dark matter, though not directly observable, are inferred from their effects on the observable universe, influencing its expansion and the formation of cosmic structures. The study of the observable universe continues to evolve, with new discoveries and technologies constantly expanding our understanding of the cosmos and pushing the boundaries of what we can see. Observing the universe comes with several limitations that scientists must work around. One major limitation is the speed of light. Because light travels at a finite speed, we can only see objects whose light has had time to reach us, limiting our view to the observable universe. Another limitation is the age of the universe. We can only observe events that have occurred since the Big Bang, about 13.8 billion years ago. Anything that happened before this is beyond our observational capabilities. The expansion of the universe also complicates observations. As the universe expands, distant objects move away from us, making their light red-shifted and fainter, which can be challenging to detect. Interstellar dust and gas can obscure our view, particularly within our own galaxy. This cosmic material absorbs and scatters light, making it difficult to see objects behind these clouds. Our atmosphere poses another challenge. Atmospheric turbulence can distort the light from celestial objects, affecting the clarity of ground-based telescopic observations. This is why many observatories are placed on high mountains or in space. Telescopes have their own limitations in terms of resolution and sensitivity. Even the most advanced telescopes can only see so far and so clearly, depending on their design and the wavelengths of light they observe. The finite lifetime of telescopes and instruments is another issue. Over time, equipment degrades and becomes outdated, requiring constant innovation and replacement to keep up with observational demands. The vast distances involved mean that even light takes billions of years to travel, so we are always looking into the past. This time delay means we can't observe the universe as it is now, but only as it was. Cosmic rays and other high-energy particles can interfere with observations, especially those involving sensitive instruments in space. These particles can create noise and distort data. Observational biases also play a role. We can only observe the universe from our position in space, leading to potential biases in our understanding of the cosmos. This is sometimes called the selection effect. The limits of current technology restrict our ability to detect faint or distant objects. As technology improves, we hope to observe further and with greater detail, but there will always be limits to what we can see. Data interpretation presents another challenge. The data we collect needs to be processed and analyzed, often involving complex models and assumptions that can introduce uncertainties. Human error is an ever-present risk. Mistakes in calibration, data collection, or analysis can lead to incorrect conclusions, highlighting the importance of rigorous scientific methods and peer review. Funding and resource limitations also constrain observational projects. Building and maintaining advanced telescopes and space missions require significant investment, and financial limitations can impact the scope and scale of research. Finally, theoretical limitations affect our understanding. Our current theories and models may not fully explain all observed phenomena, requiring continuous revision and sometimes completely new theories to make sense of the data we collect. Astronomers use a variety of methods to observe the universe, each suited to different types of objects and phenomena. One primary method is optical telescopes, which collect visible light from celestial objects and magnify them for detailed study. Radio telescopes are another crucial tool. They detect radio waves emitted by distant stars, galaxies, and other cosmic sources, allowing astronomers to study objects that are not visible in optical wavelengths. Space telescopes overcome the limitations of Earth's atmosphere by operating in orbit. Instruments like the Hubble Space Telescope provide clear, unobstructed views of the universe in multiple wavelengths, from ultraviolet to infrared. Infrared telescopes detect heat emitted by celestial objects. This capability is essential for observing regions obscured by dust, such as star-forming nebula, and for studying the early universe. X-ray telescopes like the Chandra X-ray Observatory observe high-energy phenomena such as black holes, neutron stars, and supernova remnants. These telescopes capture X-rays that cannot penetrate Earth's atmosphere. Gravitational wave detectors, such as LIGO and Virgo, measure ripples in spacetime caused by violent cosmic events like merging black holes and neutron stars. These observations provide insights into phenomena that are otherwise invisible. Spectroscopy is a technique used to analyze the light from celestial objects. By studying the spectrum of light, astronomers can determine the composition, temperature, motion, and other properties of stars and galaxies. Astronomers also use photometry to measure the brightness of objects over time. This method helps in studying variable stars, exoplanets, and the changes in brightness due to supernovae or other transient events. Direct imaging of exoplanets involves blocking the light from a star to see its surrounding planets. This technique is challenging, but has been successful in capturing images of distant worlds. Microlensing occurs when a massive object passes between us and a distant star, magnifying the star's light. This method is useful for detecting exoplanets and dark matter. Astrometry involves precise measurements of the positions and movements of stars. This technique can reveal the presence of unseen companions, such as exoplanets, by detecting slight wobbles in a star's motion. Neutrino observatories detect nearly massless particles, produced by nuclear reactions in stars, supernovae, and other cosmic events. These observatories, like the IceCube Neutrino Observatory, help study high-energy processes in the universe. Cosmic microwave background, CMB, observations involve measuring the residual radiation from the Big Bang. Satellites like Planck have mapped the CMB in great detail, providing insights into the early universe's conditions. Time-domain astronomy focuses on studying objects that change over time, such as supernovae, gamma-ray bursts, and variable stars. This approach helps understand the dynamic processes in the universe. Finally, multi-messenger astronomy combines data from different types of observations, such as electromagnetic waves, gravitational waves, and neutrinos. This comprehensive approach provides a more complete picture of cosmic events and their underlying physics. Theories about the unobservable universe aim to explain what lies beyond the limits of what we can see. One prominent theory is the concept of the multiverse. This suggests that our universe is just one of many, potentially infinite universes existing simultaneously. Another theory is eternal inflation. This idea proposes that the rapid expansion of the universe during the Big Bang didn't stop uniformly but continues in different regions, creating countless bubble universes that are separate from ours. The holographic principle is another fascinating theory. It posits that our three-dimensional universe might be a projection of information encoded on a distant, two-dimensional surface, implying that what we perceive could be an illusion. String theory introduces the idea of multiple dimensions beyond the familiar three of space and one of time. These extra dimensions could be compactified or infinitely large, influencing the structure and behavior of the unobservable universe. Loop quantum gravity offers a different perspective, suggesting that space-time itself is quantized. This theory implies that at the smallest scales, space and time are made up of discrete loops, which could have profound implications for the nature of the unobservable universe. The concept of parallel universes within quantum mechanics suggests that every possible outcome of every event actually occurs in separate, branching universes. This idea extends our universe into an infinite tree of possibilities. Some theories propose that our universe is part of a larger, higher-dimensional space called the bulk. In this view, our universe could be a three-dimensional brain floating within this higher-dimensional space. Another intriguing theory is the idea of a cyclic universe. This suggests that the universe goes through endless cycles of big bangs and big crunches, with each cycle representing a new iteration of the universe. Dark matter and dark energy are components of the unobservable universe that profoundly affect its structure and evolution. These mysterious substances make up most of the universe's mass-energy content, yet remain invisible and undetectable except through their gravitational effects. The concept of cosmic strings offers another explanation for the unobservable universe. These are hypothetical one-dimensional defects in space-time that could stretch across the entire universe, influencing its shape and behavior in ways we can't directly observe. The theory of primordial black holes suggests that tiny black holes formed in the early universe might exist in large numbers, contributing to dark matter and affecting the structure of the unobservable universe. Some scientists speculate about the existence of other forms of matter and energy that we cannot currently detect. These unknown forms could interact with our universe in subtle ways, shaping the unobservable cosmos. The anthropic principle proposes that the universe's properties are fine-tuned for the existence of life. In an infinite multiverse, different regions could have different physical constants, and we happen to live in one where conditions are just right for life. Gravitational wave observations are beginning to provide hints about the unobservable universe. These waves carry information about violent cosmic events and could eventually reveal details about regions beyond our observational reach. Finally, advancements in theoretical physics and technology continually push the boundaries of our understanding. As we develop new tools and theories, we may uncover more about the unobservable universe, shedding light on its mysteries and expanding our knowledge of the cosmos. The concept of an infinite universe carries profound implications for our understanding of reality. If the universe is infinite, it challenges the notion of a definitive edge or boundary in space. One implication is that if space is infinite, it could mean that everything that can happen has happened, or will happen somewhere in the universe. This raises intriguing possibilities about the existence of other life forms and civilizations. Infinity in the universe also suggests that there could be an infinite number of stars, planets, and galaxies. This idea vastly expands the scope of astronomical research and the potential for discovery. The concept of infinity impacts our understanding of cosmology. Traditional models that focus on a finite universe need to be adjusted to consider the implications of an endless cosmos. With an infinite universe, the idea of parallel worlds or alternate realities becomes more plausible. Every possible configuration of matter could exist somewhere, leading to an endless array of parallel universes. Infinity affects our perception of time as well. If the universe is infinite, then time could also stretch infinitely into the past and future, altering our understanding of temporal existence. The idea of an infinite universe challenges our understanding of physics. The laws of physics as we know them might behave differently in different parts of an infinite universe, potentially varying across vast distances. The concept of entropy, which measures disorder, also faces new questions in an infinite universe. If the universe is infinite, entropy may never reach a maximum, suggesting ongoing cycles of creation and destruction. The infinite universe brings about philosophical questions regarding the meaning and significance of life. In an endless cosmos, our place within it becomes a point of deep reflection and contemplation. Infinity in the universe implies that our observable universe is just a tiny fraction of a much larger reality. This humbling perspective reshapes our understanding of the cosmos and our role within it. The vastness of an infinite universe affects our approach to space exploration. With no boundaries, the potential for discovery is limitless, driving the quest for knowledge and advancement in technology. The idea of an infinite universe impacts the way we think about distance and travel. Reaching any specific point in an infinite cosmos becomes a complex challenge, involving potentially endless journeys. An infinite universe suggests that the multiverse theory, which posits the existence of many universes, each with different physical constants and laws, could be a reality. The infinite scale of the universe also has implications for quantum mechanics. Infinite possibilities at the quantum level might lead to new interpretations of particle behavior and fundamental forces. Ultimately, the concept of an infinite universe pushes the boundaries of human imagination and understanding, inviting us to rethink our place in the cosmos and the nature of reality itself. Cosmologists use three main models to describe the universe's shape: open, closed, and flat. Each model has different implications for the universe's geometry and ultimate fate. An open universe is one that will expand forever. It has a saddle-shaped geometry, meaning that parallel lines will eventually diverge. In this model, the universe does not have enough mass to stop its expansion, leading to an endless increase in size. A closed universe, on the other hand, is finite in size but unbounded, much like the surface of a sphere. In this model, the universe has enough mass to eventually stop its expansion and begin contracting, potentially leading to a big crunch. The flat universe model suggests that the universe is infinite and will expand forever, but the expansion rate will slow down over time, approaching zero but never actually stopping. This model implies a balance between the density of matter and the expansion rate. The geometry of a flat universe is like a sheet of paper, where parallel lines remain parallel. This model is supported by current observations, particularly measurements of the cosmic microwave background radiation. In an open universe, the curvature is negative, resembling a saddle. This leads to interesting implications for the paths of light and the formation of large-scale structures like galaxies and clusters. In a closed universe, the positive curvature means that if you travel far enough in one direction, you could eventually end up back where you started. This has fascinating implications for the universe's topology and our understanding of space. A flat universe has zero curvature, meaning that Euclidean geometry applies on a large scale. This simplifies many cosmological calculations and aligns with most current observational data. Each of these models has different implications for the universe's fate. An open universe will continue to expand forever, becoming increasingly cold and empty as galaxies move further apart. A closed universe will eventually stop expanding and begin to contract, potentially leading to a cyclical model where the universe goes through repeated cycles of big bangs and big crunches. In a flat universe, the expansion will continue forever but at a decreasing rate. This model suggests a more stable long-term future compared to the other two scenarios. The cosmic microwave background radiation provides key evidence for determining the universe's shape. Detailed measurements by satellites like Planck have shown that the universe is very close to flat, with only slight deviations possible. Dark energy plays a crucial role in these models. It is the mysterious force driving the accelerated expansion of the universe. The effects of dark energy need to be considered when predicting the ultimate fate of the universe. Current data suggest that the universe is flat with a slight curvature, but the exact nature of dark energy and its long-term effects remain areas of active research. Understanding the universe's shape helps cosmologists make predictions about its future, the formation of structures within it, and the fundamental nature of space and time. These models are essential for our ongoing exploration of the cosmos. Dark matter and dark energy are two of the most mysterious and significant components of the universe. Together, they make up about 95% of the total mass-energy content of the cosmos. Dark matter is an invisible form of matter that does not emit, absorb, or reflect light. It interacts with regular matter through gravity, influencing the structure and behavior of galaxies and clusters. The existence of dark matter was first inferred from the rotational speeds of galaxies. Observations showed that the outer regions of galaxies rotate faster than expected, suggesting the presence of unseen mass. Gravitational lensing provides further evidence for dark matter. When light from distant objects passes near a massive object, it bends, creating multiple images or distortions. The amount of lensing observed cannot be explained by visible matter alone. Dark matter also plays a crucial role in the formation and growth of cosmic structures. Its gravitational pull helps clump together gas and dust, leading to the formation of stars, galaxies, and clusters. While dark matter is critical to our understanding of the universe, its exact nature remains unknown. It could be composed of hypothetical particles such as WIMPs or axions, but direct detection has yet to be achieved. Dark energy, on the other hand, is an unknown form of energy that permeates space and accelerates the expansion of the universe. Its discovery came from observations of distant supernovae in the late 1990s. These observations showed that the universe's expansion is not slowing down as previously thought, but speeding up. This acceleration suggests the presence of a repulsive force counteracting gravity, known as dark energy. The effects of dark energy become more pronounced as the universe expands. Over time, it could lead to scenarios where galaxies move further apart, eventually becoming isolated in the vastness of space. The cosmological constant introduced by Einstein is one explanation for dark energy. It represents a constant energy density filling space homogeneously. However, the true nature of dark energy could be more complex. Another possibility is that dark energy is dynamic, changing over time. This idea is explored through theories such as quintessence, which propose a field that evolves and affects the universe's expansion rate. The interplay between dark matter and dark energy shapes the fate of the universe. While dark matter pulls structures together, dark energy drives them apart. The balance between these forces determines cosmic evolution. Understanding dark matter and dark energy is one of the biggest challenges in modern cosmology. Experiments and observations, such as those conducted by the Large Hadron Collider and space telescopes, aim to uncover their properties. These mysterious components highlight the limitations of our current knowledge. They remind us that much of the universe remains unseen and unexplained, driving the quest for new theories and discoveries. As we continue to explore the cosmos, dark matter and dark energy will remain key focal points. Unlocking their secrets could revolutionize our understanding of the universe and its fundamental nature. The mathematical foundations of cosmology are crucial for understanding the universe. These foundations include a range of equations and models that describe the behavior of space, time, and matter on cosmic scales. Einstein's theory of general relativity is central to modern cosmology. The field equations of general relativity describe how matter and energy influence the curvature of space-time, which in turn affects the motion of objects. The Friedmann equations are derived from general relativity and are used to model the expansion of the universe. These equations take into account the density of matter, radiation, and dark energy to describe how the universe evolves over time. The Robertson-Walker metric is a solution to Einstein's equations that describes a homogeneous and isotropic universe. This metric forms the basis for the standard model of cosmology, known as the lambda CDM model. The cosmological constant, represented by lambda in the lambda CDM model, is a term in Einstein's equations that accounts for dark energy. It provides a mathematical framework for understanding the accelerated expansion of the universe. The metric tensor is a mathematical object used in general relativity to describe the geometry of space-time. It encodes information about distances and angles in the curved space-time of the universe. Tensor calculus is a mathematical tool used extensively in cosmology. It allows for the manipulation of tensors, which are multi-dimensional arrays of numbers that generalize scalars and vectors to higher dimensions. The Boltzmann equation is used in statistical mechanics to describe the distribution of particles in a gas. In cosmology, it helps model the behavior of particles in the early universe and their interactions. Perturbation theory is used to study small deviations from a known solution. In cosmology, it is applied to understand the formation of structures in the universe, such as galaxies and clusters, from initial density fluctuations. The Poisson equation is used to relate the gravitational potential to the density of matter. It is essential for modeling the gravitational fields of structures within the universe. The Schrödinger equation, fundamental to quantum mechanics, also plays a role in cosmology. It helps describe the behavior of particles on very small scales and the early universe's quantum state. The Wheeler-DeWitt equation is an attempt to unify general relativity and quantum mechanics. It aims to describe the quantum state of the entire universe, though a complete theory of quantum gravity remains elusive. Fourier analysis is a mathematical technique used to decompose functions into their constituent frequencies. In cosmology, it helps analyze the cosmic microwave background radiation and the distribution of galaxies. The Hamiltonian formalism is used in both classical and quantum mechanics to describe the evolution of systems over time. It provides a powerful framework for understanding the dynamics of the universe. Non-Euclidean geometry, developed by mathematicians like Gauss and Riemann, is essential for describing the curved space-time of general relativity. It allows cosmologists to understand how the universe's shape influences its behavior and evolution. These mathematical foundations provide the tools and frameworks needed to model the universe's past, present, and future. They enable cosmologists to make predictions, test theories, and deepen our understanding of the cosmos. Different cosmological models make various predictions about the universe's behavior and fate. The Big Bang model predicts that the universe began from a hot, dense state and has been expanding ever since. This model explains the cosmic microwave background radiation and the distribution of light elements. The inflationary model extends the Big Bang theory, proposing a brief period of rapid expansion shortly after the Big Bang. This predicts a flat universe with uniform temperature, consistent with observations of the cosmic microwave background. The lambda CDM model, which includes dark energy, represented by the cosmological constant lambda, predicts the accelerated expansion of the universe. This model explains the large-scale structure of the universe and the observed acceleration in the expansion rate. In an open universe model, the universe will expand forever. This model predicts that galaxies will continue moving apart, leading to an increasingly cold and empty cosmos. A closed universe model predicts that the universe's expansion will eventually halt and reverse, leading to a contraction and possibly a big crunch. This model suggests a cyclical nature to cosmic events. The flat universe model predicts an eternal expansion that gradually slows but never completely stops. This model fits with the current observations of the universe's geometry and expansion rate. String theory predicts the existence of additional dimensions beyond the familiar 3 of space and 1 of time. These extra dimensions could influence the behavior of fundamental particles and the overall structure of the universe. Loop quantum gravity predicts that space-time is quantized at the smallest scales. This model suggests that the universe could have undergone a bounce, avoiding a singularity at the Big Bang, and leading to cyclical expansions and contractions. The multiverse theory predicts that our universe is just one of many. These parallel universes could have different physical constants and laws, resulting in a vast array of possible realities. The holographic principle predicts that the information within a volume of space can be described by data on its boundary. This model has implications for black holes and the nature of quantum gravity. The cyclic model predicts that the universe undergoes repeated cycles of expansion and contraction. This model suggests that the Big Bang was not the beginning, but a transition between cycles. The anthropic principle predicts that the universe's physical constants are fine-tuned to allow for the existence of life. This principle is often used to explain why our universe appears to be uniquely suited for life. The dark energy models predict various scenarios for the universe's future. Some suggest that dark energy's influence will increase, leading to a big rip where galaxies, stars, and even atoms are torn apart. The ekpyrotic model predicts that the universe was formed from the collision of two brains in higher dimensional space. This model offers an alternative to the traditional Big Bang and inflationary theories. The conformal cyclic cosmology predicts that the universe goes through infinite cycles, with each cycle beginning with a Big Bang and ending in a smooth, empty state. This model suggests a timeless, eternal cosmos. Current observational support for cosmological models comes from a variety of sources. The cosmic microwave background radiation, detected by satellites like COBE, WMAP, and Planck, provides a snapshot of the early universe, confirming predictions of the Big Bang and inflationary models. The distribution of galaxies and large-scale structures observed in the universe aligns with predictions from the Lambda CDM model. Surveys like the Sloan Digital Sky Survey map these structures, supporting the idea of dark matter and dark energy. Observations of Type Ia supernovae reveal that the universe's expansion is accelerating. This discovery provided strong evidence for dark energy, and was a major breakthrough in understanding the universe's expansion dynamics. Gravitational lensing, where light from distant objects is bent by massive foreground objects, supports the existence of dark matter. The degree of lensing observed cannot be explained by visible matter alone, indicating a significant amount of unseen mass. The study of galaxy rotation curves further supports dark matter. The outer regions of galaxies rotate faster than can be accounted for by visible matter, implying the presence of dark matter to explain the observed dynamics. Measurements of the Hubble constant, which describes the universe's expansion rate, come from various methods including Cepheid variable stars and redshift data. These measurements provide crucial data for refining cosmological models. The isotropy and homogeneity of the cosmic microwave background suggest a universe that is uniform on large scales, consistent with predictions from inflationary theory. Tiny fluctuations in this background radiation also provide clues about the universe's initial conditions. Observations of the cosmic microwave background polarization offer insights into the early universe's conditions and the nature of cosmic inflation, providing additional support for inflationary models. Studies of the intergalactic medium, the diffuse gas between galaxies, provide information about the distribution of matter in the universe. Observations using the Lyman alpha forest technique support the existence and distribution of dark matter. The detection of gravitational waves by LIGO and Virgo has opened a new window for observing the universe. These observations confirm predictions from general relativity and provide new ways to study cosmic events like black hole mergers. Direct imaging of exoplanets and the study of their atmospheres help refine models of planet formation and the conditions necessary for life, contributing to our broader understanding of the universe. The observation of high-energy cosmic rays and neutrinos gives information about energetic processes in the universe, such as supernovae and active galactic nuclei, supporting models of stellar and galactic evolution. Infrared and ultraviolet observations provide data on the formation and evolution of stars and galaxies. These wavelengths can penetrate dust clouds, revealing details about star-forming regions and the life cycle of stars. The study of dark energy using large-scale surveys like the Dark Energy Survey and the upcoming Euclid mission aims to understand the nature of this mysterious force driving the universe's accelerated expansion. Finally, continuous advancements in technology and observational techniques promise to refine our understanding of the universe. Each new discovery adds to the body of evidence supporting existing models or challenges them, driving the evolution of cosmological theories. SpaceTime is the four-dimensional fabric that combines the three dimensions of space with the dimension of time. This concept is fundamental to the theory of general relativity, developed by Albert Einstein. In general relativity, space-time is not a passive backdrop, but an active participant in the dynamics of the universe. Massive objects like stars and planets cause a curvature in space-time, which we perceive as gravity. Imagine space-time as a flexible, elastic sheet. When a heavy object like a bowling ball is placed on this sheet, it creates a depression. Smaller objects, like marbles, will roll towards the bowling ball, mimicking the effect of gravity. This curvature of space-time affects the path of objects moving through it. Light, although traveling in a straight line, will follow the curved space-time around massive objects, a phenomenon known as gravitational lensing. The presence of mass and energy determines how space-time is curved. This relationship is described by the Einstein field equations, a set of 10 interrelated differential equations. One of the key predictions of general relativity is that time runs slower in stronger gravitational fields. This effect, known as gravitational time dilation, has been confirmed by experiments and observations, such as the precise timing of GPS satellites. Space-time can also be warped by the motion of massive objects. When such objects accelerate, they can create ripples in the fabric of space-time, known as gravitational waves. These waves have been detected by observatories like LIGO. In the context of the universe, space-time is dynamic and expanding. The Big Bang theory describes how space-time itself began to expand from a highly dense and hot initial state, leading to the universe we observe today. The expansion of space-time means that galaxies are moving away from each other. This expansion is not because the galaxies are traveling through space, but because the space between them is increasing. Black holes represent extreme warping of space-time. Inside a black hole, the curvature becomes so severe that not even light can escape. The boundary of this region is known as the event horizon. Space-time near a rotating black hole can become twisted, dragging space and time around with it. This phenomenon, called frame dragging, has been observed around massive rotating objects like neutron stars. The concept of space-time also introduces the idea of space-time intervals, which remain invariant regardless of the observer's motion. This invariance forms the basis of the theory of special relativity. Special relativity, a precursor to general relativity, describes how space and time are relative and depend on the observer's state of motion. It introduces the concept that the speed of light is constant in all reference frames. In special relativity, as objects approach the speed of light, time for them slows down and lengths contract. These effects have been confirmed by numerous experiments, such as the behavior of particles in accelerators. Understanding space-time is essential for modern physics and cosmology. It underpins the theories that explain the large-scale structure of the universe, the behavior of celestial objects, and the fundamental nature of reality itself. Einstein's theory of relativity revolutionized our understanding of space, time, and gravity. It consists of two parts: special relativity and general relativity. Special relativity, published in 1905, addresses the physics of objects moving at constant speeds, particularly those moving close to the speed of light. It introduces the concept that the laws of physics are the same for all non-accelerating observers. One of the key principles of special relativity is that the speed of light is constant in all inertial reference frames. This leads to counterintuitive phenomena such as time dilation and length contraction. Time dilation means that time passes more slowly for an object moving close to the speed of light compared to one at rest. This effect has been confirmed by experiments with fast-moving particles and precise clocks on airplanes. Length contraction states that objects moving at high speeds will appear shorter in the direction of motion to a stationary observer. This phenomenon also arises from the constancy of the speed of light. Special relativity also introduces the concept of space-time, a four-dimensional continuum that combines three spatial dimensions with one time dimension. Events that occur in space and time are interconnected in this framework. The famous equation E = mc2 emerges from special relativity, showing that mass and energy are interchangeable. This equation explains why a small amount of mass can be converted into a large amount of energy, as seen in nuclear reactions. General relativity, published in 1915, extends these concepts to include gravity. It describes gravity not as a force, but as the curvature of space-time caused by mass and energy. According to general relativity, massive objects like stars and planets warp the fabric of space-time around them. This curvature influences the paths of objects and light, leading them to follow curved trajectories. One of the predictions of general relativity is the bending of light by gravity, known as gravitational lensing. This effect has been observed in multiple instances, confirming the theory's accuracy. General relativity also predicts the existence of black holes, regions where space-time curvature becomes so extreme that not even light can escape. Black holes have been detected through their interactions with surrounding matter and gravitational waves. Another key prediction is gravitational time dilation, where time runs slower in stronger gravitational fields. This effect has practical implications, such as the need to account for it in the operation of GPS satellites. Gravitational waves, ripples in spacetime caused by accelerating massive objects, are another prediction of general relativity. These waves were directly detected for the first time in 2015, a century after Einstein predicted them. General relativity has passed numerous experimental tests and is crucial for understanding cosmic phenomena. It underpins modern cosmology, the study of black holes, and the behavior of light in strong gravitational fields. Einstein's theory of relativity transformed our understanding of the universe, providing a new framework for exploring the cosmos and the fundamental nature of space, time, and gravity. Gravity is one of the fundamental forces in the universe, playing a crucial role in shaping the cosmos. It is the force that attracts two bodies towards each other, governed by the mass of the objects and the distance between them. Sir Isaac Newton first formulated the law of universal gravitation in the 17th century. Newton's law states that every mass exerts an attractive force on every other mass. This force is proportional to the product of their masses, and inversely proportional to the square of the distance between them. Newton's law explained many physical phenomena, from the falling of an apple to the orbits of planets around the Sun. It provided a framework for understanding how gravity operates on Earth and throughout the solar system. However, Newton's theory had limitations, particularly in explaining the precise orbit of Mercury and the behavior of light in a gravitational field. These issues were later addressed by Einstein's general theory of relativity. In Einstein's general relativity, gravity is not seen as a force but as the curvature of space-time caused by mass and energy. Massive objects like stars and planets create dents in the fabric of space-time, and other objects move along these curves. This curvature explains why planets orbit the Sun in elliptical paths and why light bends when it passes near a massive object. The bending of light by gravity has been confirmed by observations of gravitational lensing. Gravity is responsible for the formation of structures in the universe. It caused gas and dust to collapse and form stars, planets, and galaxies. Without gravity, these structures would not exist. In the context of the universe's expansion, gravity works in opposition to the initial force of the Big Bang. While the Big Bang caused the universe to expand, gravity pulls matter together, influencing the rate of expansion. Gravity also governs the life cycle of stars. It causes the collapse of gas clouds to form stars and dictates the processes within stars, such as nuclear fusion. Eventually, gravity leads to the death of stars, forming white dwarfs, neutron stars, or black holes. In galaxies, gravity holds stars in orbit around the galactic center. The presence of dark matter inferred from gravitational effects explains why stars in the outer regions of galaxies orbit faster than expected. On Earth, gravity provides the force that keeps us anchored to the ground. It influences everything from the flow of rivers to the flight of birds and airplanes. Our daily lives are deeply affected by this fundamental force. Gravity also affects time through gravitational time dilation. Clocks run slower in stronger gravitational fields, a phenomenon that has been confirmed by experiments and is accounted for in GPS technology. The study of gravity has led to many technological advancements. Understanding gravitational forces allows us to send satellites into orbit, explore other planets, and develop technologies like gravitational wave detectors. Gravitational waves, predicted by Einstein and confirmed by LIGO, open a new way to observe the universe. They carry information about cosmic events like black hole mergers, providing insights that electromagnetic waves cannot. Gravity's influence extends beyond our universe, potentially playing a role in theories about multiple universes and higher dimensions. its fundamental nature continues to be a subject of research and discovery. Ultimately, gravity is a key force that shapes the universe. Its effects are seen from the smallest scales on Earth to the largest cosmic structures, making it a cornerstone of our understanding of the natural world. The idea of an infinite universe brings profound implications for our understanding of existence. If the universe is truly infinite, it challenges the notion of a definitive edge or boundary in space. One implication is the potential for an infinite number of stars, planets, and galaxies. This vastly expands the scope of astronomical research and the potential for discovering new celestial objects and phenomena. An infinite universe suggests that every possible configuration of matter could exist somewhere. This includes the possibility of other life forms and civilizations, each with their own unique developments and histories. The concept of infinity impacts our understanding of cosmology. Traditional models that focus on a finite universe need to be adjusted to consider the implications of an endless cosmos. Infinity implies that there could be regions of the universe beyond our observable horizon that follow different physical laws or constants. This challenges our understanding of universal principles and uniformity. With an infinite universe, the idea of parallel worlds or alternate realities becomes more plausible. Every possible scenario could play out somewhere, leading to an endless array of parallel universes. Infinity affects our perception of time as well. If the universe is infinite, then time could also stretch infinitely into the past and future, altering our understanding of temporal existence. The concept of an infinite universe challenges our understanding of physics. The laws of physics as we know them might behave differently in different parts of an infinite universe, potentially varying across vast distances. The idea of entropy, which measures disorder, faces new questions in an infinite universe. If the universe is infinite, entropy may never reach a maximum, suggesting ongoing cycles of creation and destruction. The infinite universe brings about philosophical questions regarding the meaning and significance of life. In an endless cosmos, our place within it becomes a point of deep reflection and contemplation. Infinity in the universe implies that our observable universe is just a tiny fraction of a much larger reality. This humbling perspective reshapes our understanding of the cosmos and our role within it. The vastness of an infinite universe affects our approach to space exploration. With no boundaries, the potential for discovery is limitless, driving the quest for knowledge and advancement in technology. The idea of an infinite universe impacts the way we think about distance and travel. Reaching any specific point in an infinite cosmos becomes a complex challenge, involving potentially endless journeys. An infinite universe suggests that the multiverse theory, which posits the existence of many universes, each with different physical constants and laws, could be a reality. The infinite scale of the universe also has implications for quantum mechanics. Infinite possibilities at the quantum level might lead to new interpretations of particle behavior and fundamental forces. Ultimately, the concept of an infinite universe pushes the boundaries of human imagination and understanding, inviting us to rethink our place in the cosmos and the nature of reality itself. Space-time is a fundamental concept in different cosmological models, each providing unique perspectives on the nature of the universe. In the Big Bang model, space-time began from a singularity and has been expanding ever since, shaping the universe's large-scale structure. The inflationary model adds a period of rapid exponential expansion to the Big Bang, smoothing out irregularities in space-time and explaining the universe's uniformity and flatness. This model suggests that space-time itself underwent a phase transition, stretching incredibly fast. In the lambda CDM model, space-time continues to expand, driven by dark energy. This model incorporates the cosmological constant, lambda, which acts as a repulsive force, causing the accelerated expansion of the universe. String theory introduces additional dimensions beyond the familiar four of space-time. These extra dimensions could be compactified or large, influencing the behavior of fundamental particles and the fabric of space-time itself. Loop quantum gravity proposes that space-time is quantized at the smallest scales, consisting of discrete loops. This model suggests that the continuum of space-time breaks down at the Planck scale, potentially avoiding singularities like those in black holes and the Big Bang. In the multiverse theory, our universe's space-time is just one of many, each with its own distinct properties and laws of physics. These multiple spacetimes could be connected through higher dimensional space or exist independently. The cyclic model posits that spacetime undergoes repeated cycles of expansion and contraction. In this view, the Big Bang is not a singular event, but part of an endless sequence, with spacetime reborn after each big crunch. The holographic principle suggests that the information within a volume of space can be described by data on its boundary. This idea implies that our three-dimensional universe could be a projection of information encoded on a distant, two-dimensional surface. General relativity describes how spacetime is curved by mass and energy, creating the gravitational effects we observe. This curvature determines the motion of objects and the propagation of light in the universe. In special relativity, spacetime is a flat, four-dimensional continuum where the speed of light is constant for all observers. This model introduces the concept that space and time are relative, depending on the observer's motion. Black holes represent regions of extreme spacetime curvature. Inside a black hole, spacetime becomes so warped that not even light can escape, leading to an event horizon that marks the boundary of no return. Gravitational waves are ripples in spacetime caused by accelerating massive objects. Their detection confirms general relativity's predictions and provides a new way to observe the universe's most violent events. The expanding universe model describes how spacetime itself is stretching, causing galaxies to move apart. This expansion is uniform on large scales, leading to the observed redshift of distant galaxies. In the context of dark matter, spacetime is influenced by unseen mass that shapes the gravitational potential wells in which galaxies and clusters form and evolve. This dark matter interacts with spacetime through gravity, affecting cosmic structures. Finally, the role of dark energy in cosmological models highlights the dynamic nature of spacetime. Dark energy drives the accelerated expansion, suggesting that spacetime is not static, but continually evolving, shaping the universe's ultimate fate. The multiverse theory suggests that our universe is just one of many, potentially infinite universes that exist. These universes together comprise what is known as the multiverse. Each universe within the multiverse is called a parallel universe or an alternate universe. These universes can have different physical laws, constants, and conditions. The concept of the multiverse arises from several areas of physics and cosmology. One key idea comes from inflationary theory, which proposes that during the rapid expansion of the early universe, different regions could have stopped inflating at different times, creating bubble universes. Another source of the multiverse idea comes from string theory. String theory predicts the existence of multiple dimensions and suggests that our universe could be one of many three-dimensional slices within a higher dimensional space. The many worlds interpretation of quantum mechanics also supports the multiverse concept. It proposes that every quantum event results in a branching of the universe, creating a new parallel universe for each possible outcome. These parallel universes could be vastly different from our own, with different forms of matter, different physical constants, and even different laws of physics. Some might be similar to our universe, while others could be completely alien. The multiverse theory helps to address certain fine-tuning problems in physics. For example, why do the physical constants in our universe have the precise values needed to support life? In a multiverse, every possible set of constants might exist somewhere. One implication of the multiverse is that there could be other versions of you, living different lives based on different choices or circumstances. This idea, though speculative, is a fascinating aspect of the theory. Evidence for the multiverse is indirect and largely theoretical at this point. Observations of cosmic microwave background radiation and the large-scale structure of the universe provide some hints, but direct proof remains elusive. Critics of the multiverse theory argue that it is untestable and hence not a scientific theory in the traditional sense. Without the ability to observe or interact with other universes, it remains a speculative idea. Despite these criticisms, the multiverse theory is taken seriously by many physicists and cosmologists. It offers a potential framework for understanding the fundamental nature of reality. If the multiverse exists, it would mean that the universe we observe is just a small part of a much larger and more complex structure. This has profound implications for our understanding of existence. The multiverse theory also challenges our notion of uniqueness. In a multiverse, our universe is not special. It is just one of countless others, each with its own unique properties. Research into the multiverse is ongoing, with new theories and models being developed. Advances in technology and observations may one day provide more concrete evidence for or against the existence of other universes. Understanding the multiverse could revolutionize our understanding of the cosmos and our place within it. It pushes the boundaries of human knowledge and challenges us to rethink what we know about reality. There are several types of multiverses proposed by different theories, each with unique characteristics. One type is the bubble universe, which arises from the theory of eternal inflation. In this model, our universe is one of many bubbles that have formed in an ever-expanding cosmic foam. Another type is the parallel universe, which comes from the many worlds interpretation of quantum mechanics. According to this idea, every possible outcome of a quantum event creates a new, branching universe, leading to an infinite number of parallel realities. In these parallel universes, different versions of events play out, resulting in countless alternate histories and futures. For example, in one universe you might have taken a different career path, leading to a completely different life. The brain multiverse theory comes from string theory. It suggests that our universe is a three-dimensional brain existing within a higher dimensional space. Other brains, each representing a separate universe, could exist in this higher dimensional space, possibly interacting through gravity or other forces. The cyclic multiverse proposes that the universe goes through infinite cycles of big bangs and big crunches. In this model, the universe expands and contracts repeatedly, with each cycle giving rise to a new universe. The quantum multiverse, similar to the many worlds interpretation, posits that all possible quantum states exist simultaneously in a vast superposition. Each possible state corresponds to a different universe, all existing within a quantum multiverse. The holographic multiverse suggests that our universe is a holographic projection of information encoded on a distant, two-dimensional surface. This idea stems from the holographic principle, which has implications for black holes and quantum gravity. Another concept is the mathematical multiverse proposed by Max Tegmark. It suggests that all mathematically consistent structures exist as physical realities. In this view, every mathematical structure represents a different universe with its own laws and constants. The simulated multiverse posits that our universe is a simulation run by a more advanced civilization. In this scenario, there could be countless simulated universes, each with different rules set by the creators of the simulation. The landscape multiverse arises from string theory's idea of a vast landscape of possible vacuum states. Each vacuum state corresponds to a different universe with its own unique physical properties, creating a multiverse of diverse environments. The ultimate ensemble theory suggests that all possible universes exist, each representing a different set of physical laws and constants. This concept implies an infinite variety of universes, each exploring different aspects of reality. The mirror multiverse proposes the existence of a parallel universe that mirrors our own, with particles and forces that are the exact opposite of those in our universe. This idea could explain certain symmetries observed in particle physics. The black hole multiverse theory suggests that new universes are born inside black holes. Each black hole could contain a singularity that gives rise to a new universe with its own unique properties, creating a branching tree of universes. Exploring these different types of multiverses expands our understanding of the cosmos and challenges us to consider the vastness and complexity of reality beyond our observable universe. Scientific evidence and theories provide the foundation for our understanding of the universe and its potential infinity. One major piece of evidence supporting the Big Bang theory is the cosmic microwave background radiation, a faint glow left over from the early universe. The discovery of the cosmic microwave background radiation by Arno Penzias and Robert Wilson in 1965 was a breakthrough that confirmed predictions made by the Big Bang model. This radiation provides a snapshot of the universe when it was just 380,000 years old. Observations of the redshift of distant galaxies also support the Big Bang theory. Edwin Hubble discovered that galaxies are moving away from us, indicating that the universe is expanding, a key prediction of the Big Bang. The abundance of light elements such as hydrogen, helium, and lithium matches the predictions of Big Bang nucleosynthesis. These elements were formed in the first few minutes after the Big Bang, providing further evidence for this model. General relativity proposed by Albert Einstein has been confirmed by numerous experiments and observations. This theory describes how gravity affects the fabric of space-time and has been essential in understanding the large-scale structure of the universe. Gravitational lensing, the bending of light by massive objects, provides indirect evidence for dark matter. This phenomenon has been observed in many instances, confirming that there is more mass in the universe than what we can see. The detection of gravitational waves by LIGO and Virgo has opened a new window for observing the universe. These ripples in space-time are caused by violent cosmic events like black hole mergers and confirm predictions made by general relativity. Dark energy, the mysterious force driving the accelerated expansion of the universe, was discovered through observations of distant supernovae. This discovery has profound implications for the fate of the universe and our understanding of cosmology. The study of the cosmic microwave background radiation has provided detailed information about the universe's age, composition, and geometry. Measurements by satellites like COBE, WMAP, and Planck have refined our understanding of these fundamental properties. The distribution of galaxies and large-scale structures in the universe matches predictions made by cosmological models. Surveys like the Sloan Digital Sky Survey map these structures, supporting the existence of dark matter and dark energy. String theory, while still theoretical, offers a potential framework for unifying all fundamental forces of nature. It suggests the existence of multiple dimensions and provides insights into the nature of space-time and the universe's fundamental constituents. Loop quantum gravity is another theoretical approach aiming to unify general relativity and quantum mechanics. It proposes that space-time is quantized at the smallest scales, offering a different perspective on the structure of the universe. The holographic principle, stemming from studies of black holes and quantum gravity, suggests that the information within a volume of space can be described by data on its boundary. This idea has implications for our understanding of the universe's nature. The concept of the multiverse arises from various theories, including eternal inflation and string theory. These theories propose that our universe is just one of many, each with different physical laws and constants. Advancements in observational technology, such as more powerful telescopes and detectors, continue to push the boundaries of our knowledge. These tools allow scientists to gather more data, test theories, and refine our understanding of the universe and its potential infinity.
The concept of an infinite universe carries profound implications for our understanding of reality. If the universe is infinite, it challenges the notion of a definitive edge or boundary in space.
An infinite universe suggests that there could be an infinite number of stars, planets, and galaxies. This vastly expands the scope of astronomical research and the potential for discovering new celestial objects and phenomena. With infinity, the idea of repetition becomes significant. In an infinite universe, every possible arrangement of matter could occur somewhere, meaning there might be other planets identical to Earth, or even other versions of you. The concept of infinity impacts our understanding of time as well. If the universe is infinite, then time could also stretch infinitely into the past and future, altering our perception of temporal existence. Infinity implies that there could be regions of the universe beyond our observable horizon that follow different physical laws or constants. This challenges our understanding of universal principles and uniformity. The idea of entropy, which measures disorder, faces new questions in an infinite universe. If the universe is infinite, entropy may never reach a maximum, suggesting ongoing cycles of creation and destruction. An infinite universe brings about philosophical questions regarding the meaning and significance of life. In an endless cosmos, our place within it becomes a point of deep reflection and contemplation. The vastness of an infinite universe affects our approach to space exploration. With no boundaries, the potential for discovery is limitless, driving the quest for knowledge and advancement in technology. The concept of infinity challenges our understanding of physics. The laws of physics, as we know them, might behave differently in different parts of an infinite universe, potentially varying across vast distances. Infinity in the universe implies that our observable universe is just a tiny fraction of a much larger reality. This humbling perspective reshapes our understanding of the cosmos and our role within it. An infinite universe suggests that the multiverse theory, which posits the existence of many universes, each with different physical constants and laws, could be a reality. The infinite scale of the universe also has implications for quantum mechanics. Infinite possibilities at the quantum level might lead to new interpretations of particle behavior and fundamental forces. Infinity affects our perception of distance and travel. Reaching any specific point in an infinite cosmos becomes a complex challenge, involving potentially endless journeys. The idea of an infinite universe expands the boundaries of human imagination and understanding. It invites us to rethink our place in the cosmos and the nature of reality itself. Ultimately, exploring the concept of infinity pushes the limits of our knowledge and opens new avenues for scientific and philosophical inquiry, helping us to better understand the universe and our place within it. Criticisms and alternative views of the concept of an infinite universe come from various scientific and philosophical perspectives. Some scientists argue that the idea of infinity is not testable, and therefore falls outside the realm of empirical science. One major criticism is the lack of direct evidence for infinity. While we observe an expanding universe, we do not have data that confirms it is infinite. The observable universe is finite, and any claim beyond that is speculative. Philosophically, the concept of infinity raises paradoxes and challenges. The notion of an infinite universe can lead to logical contradictions, such as the idea that every possible event must occur somewhere, including highly improbable ones. Some cosmologists propose a finite universe that is unbounded, similar to the surface of a sphere. In this model, you could travel indefinitely without ever encountering an edge, but the total volume of the universe is finite. Alternative models like the cyclic universe theory suggest that the universe undergoes endless cycles of expansion and contraction. This theory does not require an infinite space or time, just perpetual cycles. The multiverse theory, while addressing some fine-tuning problems, is also criticized for being untestable. Without the ability to observe or interact with other universes, the theory remains speculative. Some argue that our understanding of physics might be incomplete, and new discoveries could provide alternative explanations that do not involve infinity. This includes advancements in quantum gravity or new fundamental particles. Critics also point out that the concept of infinity can lead to a sense of nihilism or insignificance, as it suggests an endless, impersonal cosmos. This philosophical perspective challenges human notions of meaning and purpose. The holographic principle, while offering a different view of the universe, raises its own set of challenges. It suggests that our three-dimensional reality might be an illusion, a concept that is difficult to reconcile with everyday experiences. The anthropic principle, which states that the universe must be compatible with the conscious life that observes it, is seen by some as a tautology rather than a meaningful explanation. It does not necessarily imply an infinite universe. String theory, which suggests multiple dimensions and possibly an infinite number of universes, is still a developing field. Critics argue that without experimental verification, these ideas remain speculative. Loop quantum gravity, an alternative to string theory, offers a different approach to understanding space and time. It suggests that space-time is quantized, which could imply a finite structure rather than an infinite one. Some propose that dark energy might change over time, leading to different scenarios for the universe's fate. This could result in a universe that expands, then contracts, rather than one that expands infinitely. Philosophers also challenge the idea of actual infinity, distinguishing it from potential infinity. Actual infinity is a completed, unbounded quantity, whereas potential infinity is an unending process. This distinction raises questions about the nature of the universe. Ultimately, the concept of an infinite universe remains a topic of active debate and research. As our understanding of cosmology evolves, we may find new evidence or develop new theories that reshape our views on infinity and the structure of the cosmos. Quantum mechanics is the branch of physics that deals with the behavior of particles on the smallest scales, such as atoms and subatomic particles. It challenges our classical understanding of the world, introducing concepts that often seem counterintuitive. One of the fundamental principles of quantum mechanics is wave-particle duality. This principle states that particles, such as electrons and photons, exhibit both wave-like and particle-like properties depending on how they are measured. The Heisenberg uncertainty principle is another key concept. It asserts that it is impossible to simultaneously know both the exact position and exact momentum of a particle. The more precisely one is known, the less precisely the other can be determined. Quantum mechanics also introduces the idea of quantization. Certain physical properties, such as energy, can only take on discrete values rather than a continuous range. This is seen in the energy levels of electrons in an atom. Superposition is a principle that states a particle can exist in multiple states at the same time. For example, an electron can be in a state where it is simultaneously in different locations until it is measured. Entanglement is a phenomenon where particles become interconnected such that the state of one particle instantaneously affects the state of another, no matter how far apart they are. This has been confirmed experimentally and challenges classical notions of locality. The Schrödinger equation is a fundamental equation in quantum mechanics that describes how the quantum state of a physical system changes over time. It is essential for predicting the behavior of particles in a quantum system. Quantum mechanics also relies on probability. Unlike classical mechanics, which predicts definite outcomes, quantum mechanics provides probabilities for the outcomes of measurements. This probabilistic nature is intrinsic to the theory. The concept of a wave function is central to quantum mechanics. It is a mathematical function that describes the quantum state of a particle or system. The square of the wave function's amplitude gives the probability density of finding a particle in a particular state. Measurement in quantum mechanics plays a unique role. The act of measuring a quantum system forces it into one of the possible states, a process known as wave function collapse. Before measurement, the system exists in a superposition of states. Quantum mechanics has led to the development of many technologies, such as semiconductors, lasers, and magnetic resonance imaging, MRI. These applications rely on the principles of quantum behavior at small scales. The double-slit experiment is a famous demonstration of quantum mechanics. When particles pass through two slits, they create an interference pattern typical of waves, but if observed, they behave like particles. This experiment illustrates the principle of wave-particle duality. Quantum tunneling is another fascinating phenomenon where particles can pass through barriers that would be insurmountable according to classical physics. This effect is crucial in many processes, including nuclear fusion in stars. Quantum mechanics also underpins modern theories of particle physics, including the Standard Model, which describes the fundamental particles and their interactions. It provides the framework for understanding forces at the smallest scales. Understanding quantum mechanics is essential for advancing technology and deepening our understanding of the universe. It challenges our classical intuitions and opens up new realms of possibility in both theory and application. Quantum entanglement is one of the most intriguing phenomena in quantum mechanics. When two particles become entangled, their states become linked, so that the state of one particle instantaneously affects the state of the other, regardless of the distance between them. This entanglement means that measuring one particle's state will immediately determine the state of the entangled partner. This occurs even if the particles are light years apart, a phenomenon that Albert Einstein famously referred to as spooky action at a distance. Experiments have repeatedly confirmed the reality of entanglement. These experiments involve creating pairs of entangled particles and then measuring their properties, showing correlations that cannot be explained by classical physics. Entanglement has profound implications for our understanding of information transfer and causality. It suggests that information can be instantaneously transferred across vast distances, challenging the notion that nothing can travel faster than the speed of light. Superposition is another fundamental concept in quantum mechanics. It refers to the ability of a quantum system to exist in multiple states simultaneously. For example, an electron can be in a state where it is both spinning clockwise and counterclockwise at the same time. The principle of superposition is what allows quantum computers to perform complex calculations at incredible speeds. In a classical computer, A bit can be either 0 or 1, but a quantum bit, or qubit, can be both 0 and 1 simultaneously, vastly increasing computational power. The famous thought experiment known as Schrödinger's cat illustrates the concept of superposition. In this scenario, a cat in a sealed box is both alive and dead, until an observer opens the box and looks, collapsing the superposition into one of the two possible states. Measurement plays a crucial role in both entanglement and superposition. When a quantum system is measured, the superposition collapses into a definite state, and the entangled partner state is also instantly determined. Quantum entanglement and superposition are not just theoretical curiosities. They have practical applications in developing new technologies. Quantum cryptography, for example, uses entanglement to create secure communication channels that are theoretically immune to eavesdropping. Quantum teleportation is another application, where the state of a particle is transferred from one location to another without physically moving the particle itself. This process relies on entanglement to transmit the information instantaneously. The phenomena of entanglement and superposition challenge our classical intuitions about the nature of reality. They suggest that particles do not have definite states until they are observed, and that particles can be interconnected in ways that defy classical explanations. These concepts also have implications for our understanding of space and time. Entanglement suggests that space may not be as rigidly structured as we think, and that there might be deeper hidden connections within the fabric of the universe. Researchers are exploring ways to harness these phenomena for practical use. Quantum computing is one of the most promising fields, with the potential to revolutionize industries from cryptography to materials science by leveraging the power of entanglement and superposition. Understanding quantum entanglement and superposition is essential for advancing our knowledge of the quantum world. These phenomena are at the heart of many modern physics theories and technologies, pushing the boundaries of what we know about the universe. As we continue to explore these concepts, we are likely to uncover even more surprising and revolutionary aspects of quantum mechanics, further challenging and expanding our understanding of reality. In quantum mechanics, the role of the observer is fundamentally different from that in classical physics. Observing a quantum system affects the system in a significant way, collapsing a superposition of states into a single, definite state. This phenomenon is often illustrated by the double-slit experiment. When particles like electrons are not observed, they behave like waves, creating an interference pattern. However, when they are observed, they behave like particles, and the interference pattern disappears. The observer effect suggests that the act of measurement forces a quantum system to choose a definite state. Before observation, the system exists in a superposition, representing all possible states simultaneously. This has led to various interpretations of quantum mechanics, one of which is the Copenhagen interpretation. It posits that a quantum system remains in superposition until it is observed, at which point the wave function collapses to a specific outcome. The many worlds interpretation offers a different view, suggesting that all possible outcomes of a quantum measurement actually occur, each in a separate parallel universe. In this view, the observer does not cause the collapse but becomes entangled with the observed system. The role of the observer introduces the concept of quantum decoherence. Decoherence describes how a quantum system loses its coherence or superposition due to interactions with its environment, effectively becoming classical in nature. Quantum entanglement further complicates the role of the observer. When two particles are entangled, measuring one instantly determines the state of the other, regardless of the distance between them. This raises questions about the nature of information transfer and reality. Some interpretations suggest that consciousness plays a role in the collapse of the wave function. This idea, known as the observer effect in consciousness, proposes that the conscious observer is necessary to bring a definite reality into existence. The role of the observer also has implications for the Heisenberg uncertainty principle. The act of measuring one property of a particle, such as position, inherently disturbs another property, such as momentum, highlighting the limits of precision in quantum systems. Experimental setups like the quantum eraser experiment demonstrate how information available to the observer can affect the outcome of a measurement, even after the measurement has been made, challenging our classical notions of causality and time. In quantum computing, the role of the observer is crucial. Qubits can exist in superposition and entanglement, allowing for vast computational possibilities. However, measurement collapses these states. Thus, careful manipulation and measurement are key to quantum computation. The delayed choice experiment shows that decisions made by the observer can retroactively affect the state of a quantum system, suggesting that the present can influence the past in the quantum realm. The role of the observer is also explored in quantum cosmology, where it is debated how the universe's quantum state collapses to create the reality we observe. This touches on the measurement problem and the role of observers on a cosmic scale. Understanding the role of the observer is essential for developing technologies like quantum cryptography and teleportation, where the act of measurement and the collapse of the wave function are fundamental processes. As research continues, the role of the observer remains one of the most intriguing and debated aspects of quantum mechanics, challenging our understanding of reality and the nature of existence itself. The intersection of quantum mechanics and cosmology is a fascinating area of study that seeks to understand the universe's origins, structure, and ultimate fate. Quantum cosmology applies the principles of quantum mechanics to the entire universe, exploring phenomena that classical physics cannot explain. One of the key intersections is the theory of the Big Bang. Quantum mechanics suggests that the universe began as a quantum fluctuation in a vacuum, leading to a rapid expansion known as inflation. This theory helps explain the uniformity and flatness of the universe. Inflationary theory, which incorporates quantum fluctuations, predicts the existence of a multiverse. These fluctuations can create multiple bubble universes, each with its own physical properties, contributing to the multiverse concept. The cosmic microwave background radiation, a relic from the early universe, shows slight temperature fluctuations. These fluctuations are believed to be quantum in origin, providing a link between quantum mechanics and the large-scale structure of the universe. Black holes are another intersection point. The concept of Hawking radiation, where black holes emit radiation due to quantum effects near the event horizon, combines quantum mechanics with general relativity, challenging our understanding of these enigmatic objects. Quantum mechanics also influences our understanding of dark energy and dark matter. These mysterious components make up most of the universe's mass-energy content, and their nature might be explained by quantum fields and particles. The idea of a quantum vacuum where particles constantly pop in and out of existence has implications for the energy density of the universe. This vacuum energy could be related to dark energy, driving the accelerated expansion of the universe. Quantum entanglement and the holographic principle suggest that information within a volume of space can be encoded on its boundary. This idea is used to explore the nature of black holes and the fabric of the universe itself. The study of the early universe requires quantum cosmology to understand conditions at the Planck scale, where quantum gravitational effects dominate. This period, just after the Big Bang, holds the key to unifying general relativity and quantum mechanics. String theory, which attempts to unify all fundamental forces, posits that the fundamental particles are not points, but tiny vibrating strings. This theory requires additional dimensions and provides a framework for understanding the universe's quantum aspects. Loop quantum gravity offers an alternative approach to combining quantum mechanics and general relativity. It suggests that space-time is quantized, providing insights into the universe's structure at the smallest scales and avoiding singularities like those in black holes. Quantum cosmology also explores the concept of the wave function of the universe. This theoretical framework attempts to describe the universe's quantum state, incorporating all possible histories and states into a single mathematical entity. The study of primordial gravitational waves, generated during inflation, offers another intersection. Detecting these waves would provide evidence for quantum effects in the early universe and support the inflationary model. The intersection of quantum mechanics and cosmology raises profound questions about the nature of reality, time, and space. It challenges our understanding of the universe's origins and its ultimate fate, pushing the boundaries of both fields. As research continues, this intersection promises to yield new insights and discoveries, deepening our understanding of the cosmos and the fundamental laws that govern it. The integration of quantum mechanics with cosmology remains a frontier of modern science, offering the potential to unlock the deepest mysteries of the universe. Historical philosophical views on the nature of the universe and infinity have evolved significantly over time. Ancient Greek philosophers like Pythagoras and Parmenides contemplated the nature of existence and the concept of the infinite. Pythagoras and his followers believed in a universe governed by mathematical principles. They saw numbers and their relationships as fundamental to understanding the cosmos, hinting at an early grasp of the infinite in mathematics. Parmenides, on the other hand, argued that change and multiplicity were illusions. He proposed that reality was a single, unchanging and indivisible entity, challenging the idea of a dynamic, infinite universe. Plato introduced the concept of a realm of perfect forms, existing beyond our observable reality. His idea suggested that what we perceive is only a shadow of a more profound, infinite truth. Aristotle offered a different perspective, arguing against actual infinity. He believed that while potential infinity could exist in processes that could continue indefinitely, an actual infinite quantity was impossible within the physical universe. Medieval philosophers like Thomas Aquinas integrated Aristotle's views with Christian theology. They considered the universe finite in time but infinite in the sense of its potential for divine creation and eternal existence. During the Renaissance, thinkers like Giordano Bruno revived the idea of an infinite universe. Bruno proposed that the stars were distant suns, each possibly surrounded by their own planets, suggesting a boundless cosmos. The scientific revolution brought new insights. Isaac Newton's laws of motion and universal gravitation presented a mechanistic universe that could be infinitely extended in space, though still finite in terms of observable matter. Immanuel Kant pondered the limits of human understanding. He argued that while the concept of an infinite universe might be beyond human comprehension, it remained a useful idea for framing our scientific inquiries. Georg Cantor revolutionized mathematics in the 19th century with his work on set theory and different types of infinity. Cantor demonstrated that infinities could be compared and that some infinities were larger than others, deeply influencing both mathematics and philosophy. In the 20th century, philosophers like Alfred North Whitehead and Bertrand Russell explored the implications of an infinite universe in the context of mathematical logic and metaphysics. Their work helped bridge the gap between abstract mathematics and philosophical inquiry. The existentialists, including Jean-Paul Sartre and Albert Camus, addressed infinity in terms of human existence and meaning. They considered the infinite nature of the universe as a backdrop for the individual's search for purpose and significance. Process philosophy, advocated by Whitehead, viewed the universe as a dynamic, evolving entity. This perspective embraced the idea of an infinite process of becoming, contrasting with static notions of being. Contemporary philosophers continue to grapple with the implications of an infinite universe. They explore how modern cosmological theories intersect with traditional philosophical questions about existence, knowledge, and the nature of reality. These historical philosophical views provide a rich tapestry of thought, reflecting humanity's enduring quest to understand the infinite and our place within the vast cosmos. As science progresses, these philosophical insights continue to inform and enrich our exploration of the universe. The concept of an infinite universe carries profound theological implications, touching on the nature of the divine and the relationship between creation and the Creator. Many religious traditions have pondered the idea of infinity, seeing it as a reflection of divine attributes. In Christianity, the idea of an infinite universe can be seen as a testament to God's omnipotence and omnipresence. The vastness and complexity of the cosmos may reflect the boundless nature of God's creation and His infinite wisdom. Islamic theology also embraces the concept of an infinite creator. The Quran speaks of God's creation as vast and incomprehensible, suggesting that the infinite universe is a manifestation of Allah's infinite power and knowledge. Judaism similarly views the infinite universe as an expression of God's eternal and boundless nature. The Hebrew Bible describes the heavens as declaring the glory of God, indicating that the immensity of the universe reflects the greatness of the divine. Hinduism and Buddhism both incorporate the idea of an infinite cosmos into their spiritual philosophies. Hindu cosmology describes a cyclic universe, eternally created and destroyed by the divine, reflecting an infinite process of creation. Buddhist teachings often emphasize the infinite nature of the cosmos, aligning with the concept of samsara, the cycle of birth, death, and rebirth. This endless cycle mirrors the infinite universe, suggesting a deep interconnectedness of all existence. In many indigenous and animistic traditions, the universe is seen as a living, infinite entity, imbued with spiritual significance. The vastness of the cosmos is often perceived as a reflection of the interconnectedness and continuity of life. The concept of an infinite universe can also raise questions about the uniqueness of human life and the existence of other intelligent beings. If the universe is infinite, it may contain countless other worlds with their own forms of life and civilizations, prompting theological reflections on the nature of divine revelation and salvation. The possibility of multiple universes or a multiverse adds another layer to these theological considerations. If our universe is just one of many, each with its own laws and properties, it challenges traditional notions of creation and the uniqueness of our cosmic narrative. The idea of infinity can also deepen the sense of mystery and awe in religious experience. The infinite universe, with its endless possibilities and unknowns, can inspire a profound sense of wonder and humility before the divine. Theological discussions about the infinite universe often intersect with questions about the nature of time and eternity. Many religious traditions explore the relationship between temporal existence and eternal truth, considering how the infinite cosmos fits into this dynamic. The concept of an infinite universe can also influence ethical and moral considerations. If the cosmos is boundless and interconnected, it may encourage a greater sense of responsibility for the well-being of all creation, emphasizing the moral imperative to care for the environment and each other.
In the context of eschatology, or the study of end times, the idea of an infinite universe challenges traditional narratives of cosmic finality. It prompts theologians to reconsider notions of apocalypse and renewal within an endless cosmic framework.
Ultimately, the theological implications of an infinite universe are vast and multifaceted. They invite deeper reflection on the nature of the divine, the purpose of creation, and humanity's place within the boundless expanse of the cosmos. As scientific discoveries continue to expand our understanding of the universe, these theological reflections will likely evolve, enriching the dialogue between science and spirituality, and offering new insights into the mysteries of existence. The debate over whether the universe is infinite involves numerous arguments both for and against the idea. Proponents of an infinite universe often point to the implications of the Big Bang and inflationary theories, which suggest that space could expand without bounds. One argument for an infinite universe is based on the observable expansion of space. Since the universe has been expanding since the Big Bang, it might continue to do so indefinitely, leading to an infinite expanse. Supporters also cite the uniformity of the cosmic microwave background radiation. This uniformity aligns with the idea of a vast, potentially infinite universe that has been expanding and smoothing out over billions of years. The concept of dark energy, driving the accelerated expansion of the universe, supports the possibility of an infinite universe. If dark energy continues to propel the expansion, the universe might never stop growing. Mathematical models of the universe, such as those derived from general relativity, allow for the possibility of infinite space. These models do not inherently restrict the size of the universe, leaving room for infinity. Quantum mechanics and the idea of a multiverse also support the notion of infinity. If every possible quantum state creates a new universe, the total number of universes could be infinite, suggesting that our universe might be part of this infinite multiverse. Conversely, arguments against an infinite universe often focus on the lack of direct observational evidence. While we see an expanding universe, we cannot observe beyond the observable horizon, leaving the actual size of the universe unknown. Some critics argue that the concept of an infinite universe leads to logical paradoxes. The idea that every possible event must occur somewhere in an infinite universe can create contradictions and challenges for our understanding of reality. The finite age of the universe, estimated at 13.8 billion years, suggests that the universe might be finite in size. If the universe has only been expanding for a finite time, it could have a finite volume. Philosophical arguments against infinity often draw on the limitations of human comprehension. Infinity is an abstract concept that might not correspond to physical reality, making it difficult to accept as a literal description of the universe. Some cosmologists propose models of a finite but unbounded universe, similar to the surface of a sphere. This model allows for continuous travel without encountering an edge, offering an alternative to infinity. The idea of a cyclic universe also challenges the notion of infinity. In this model, the universe undergoes endless cycles of expansion and contraction, avoiding the need for an infinite expanse by recycling the same finite space. Critics of the multiverse theory point to its lack of empirical evidence. Without the ability to observe or interact with other universes, the theory remains speculative, and its implications for an infinite universe are uncertain. Theoretical challenges also arise from the nature of dark energy. If dark energy changes over time, it could alter the expansion rate of the universe, potentially leading to a finite cosmos rather than an infinite one. Ultimately, the debate over an infinite universe remains unresolved. Both sides present compelling arguments, and ongoing research in cosmology and quantum mechanics continues to explore this profound question, seeking to uncover the true nature of the cosmos. The intersection of science and philosophy provides a rich field for exploring fundamental questions about the universe. Both disciplines seek to understand reality, though they use different methods and frameworks. Science relies on empirical evidence and testable hypotheses to build knowledge. Through observation and experimentation, scientists develop theories that explain natural phenomena and predict future outcomes. Philosophy, on the other hand, uses critical thinking and logical reasoning to explore concepts that may not be directly testable. Philosophers examine the implications of scientific findings, questioning the nature of knowledge, existence, and reality. One area where science and philosophy intersect is the study of the nature of the universe. Cosmology, for instance, uses scientific methods to investigate the origins, structure, and fate of the universe, while philosophy grapples with the broader implications of these discoveries. The debate over the infinite universe exemplifies this intersection. Scientists provide evidence and models that suggest the universe could be infinite, while philosophers consider the logical and existential implications of such a concept. The theory of relativity, developed by Albert Einstein, is another example. It revolutionized our understanding of space and time, prompting philosophical inquiries into the nature of reality and the relationship between observer and observed. Quantum mechanics also bridges science and philosophy. Its principles, like wave-particle duality and entanglement, challenge classical notions of reality and causality, leading to philosophical debates about the nature of existence and knowledge. The question of free will versus determinism illustrates this intersection. Scientific discoveries about the brain and behavior influence philosophical discussions about human agency, responsibility, and moral accountability. Ethics is another area where science and philosophy converge. Advances in technology and medicine raise ethical questions that require philosophical analysis, such as the implications of genetic engineering, artificial intelligence, and climate change. Philosophy of science examines the foundations, methods, and implications of science itself. It addresses questions about what constitutes scientific knowledge, the role of scientific paradigms, and the objectivity of scientific inquiry. Epistemology, the study of knowledge, is deeply connected to scientific practice. Scientists rely on philosophical principles to determine the validity and reliability of their findings, while philosophers analyze the nature and limits of scientific knowledge. Metaphysics, which explores the fundamental nature of reality, often intersects with scientific theories. Concepts like space, time, matter, and causality are central to both scientific and philosophical investigations. The relationship between mind and body is a classic philosophical issue that science informs. Neuroscience provides insights into how the brain functions, influencing philosophical theories about consciousness, identity, and the self. Finally, the pursuit of wisdom, a core goal of philosophy, aligns with the scientific quest for knowledge. Both disciplines, in their respective ways, seek to expand our understanding of the universe and our place within it, fostering a deeper appreciation of the complexities and mysteries of existence. Different cultures have unique perspectives on the concept of infinity, reflecting their philosophical, religious, and scientific traditions. In ancient Greek philosophy, infinity was a topic of deep interest. Philosophers like Anaximander and Pythagoras pondered the infinite nature of the cosmos and numbers. In Hinduism, infinity is deeply embedded in the spiritual and cosmological worldview. The concept of ananta signifies endlessness, often associated with the divine. The cyclical nature of time and the eternal cycles of creation and destruction reflect this infinite perspective. Buddhism also embraces the idea of infinity through the concept of samsara, the endless cycle of birth, death, and rebirth. Enlightenment, or nirvana, is seen as liberation from this infinite cycle, reaching a state beyond time and space. Chinese philosophy, particularly Taoism, views infinity as an integral aspect of the Tao, the fundamental principle that underlies the universe. The Tao is infinite, eternal, and the source of all existence, emphasizing harmony with the endless flow of nature. In Islamic thought, infinity is associated with the nature of Allah, who is eternal and boundless. The Quran speaks of God's creation as vast and infinite, reflecting his infinite power and wisdom. Islamic scholars also made significant contributions to mathematics, exploring the concept of infinity. Judaism contemplates infinity through the infinite nature of God and the endless quest for knowledge and understanding. The concept of Ein Sof in Kabbalah represents the infinite, unknowable aspect of God, highlighting the boundless nature of divine reality. Christianity often views infinity in the context of God's eternal nature and the promise of eternal life. The infinite nature of God's love and the eternal existence of the soul are central themes in Christian theology. Native American cultures frequently see infinity reflected in the natural world and the interconnectedness of all life. The cyclical patterns of nature and the idea of a continuum between past, present, and future emphasize an infinite, holistic worldview. African spiritual traditions often perceive infinity through the ancestral connection and the endless cycles of life, death, and rebirth. The continuity of life and the eternal presence of ancestors are central to many African cosmologies. In modern Western thought, influenced by scientific advancements, infinity is explored through mathematics and cosmology. The development of calculus and set theory introduced rigorous ways to understand and manipulate the concept of infinity. Mathematical infinity, as explored by Georg Cantor and others, has led to a deeper understanding of different sizes of infinity and the infinite nature of numbers and sets. This mathematical perspective influences various scientific fields, from physics to computer science. In Japanese culture, the concept of infinity is often associated with Zen Buddhism. The idea of infinite potential and the boundless nature of the mind are emphasized in Zen teachings, fostering a sense of infinite growth and enlightenment. Indigenous Australian cultures view infinity through the lens of the Dreamtime, a timeless, infinite dimension where ancestral beings created the world. This perspective integrates infinity into the very fabric of existence and cultural storytelling. Tibetan Buddhism incorporates the concept of infinity in its cosmology and spiritual practices. The infinite nature of the mind and the endless journey towards enlightenment are central themes, reflecting a deep engagement with the concept of infinity. Across cultures, infinity represents a profound and multifaceted concept. Whether through spiritual beliefs, philosophical inquiry, or scientific exploration, the idea of the infinite continues to inspire and challenge human understanding, offering a glimpse into the boundless nature of reality. Key astronomical observations have significantly advanced our understanding of the universe. One of the most crucial is the discovery of the cosmic microwave background radiation, a faint glow that fills the universe and provides a snapshot of its early state, supporting the Big Bang theory. Edwin Hubble's observation of the redshift of distant galaxies revealed that the universe is expanding. This discovery fundamentally changed our perception of the cosmos and led to the development of modern cosmology. The detailed mapping of the cosmic microwave background by satellites like COBE, WMAP, and Planck has provided insights into the universe's age, composition, and large-scale structure, confirming predictions of the Big Bang and inflationary models. The observation of gravitational waves by LIGO and Virgo has opened a new way of observing the universe. These ripples in space-time, caused by events like black hole mergers, confirm predictions made by general relativity. The discovery of exoplanets orbiting other stars has expanded our understanding of planetary systems. Techniques such as the transit method and radial velocity have revealed thousands of exoplanets, some potentially habitable. The study of dark matter through gravitational lensing and galaxy rotation curves has shown that visible matter makes up only a small fraction of the universe's total mass. Dark matter's presence is inferred from its gravitational effects on galaxies and clusters. Dark energy, which makes up about 70% of the universe's energy density, was discovered through observations of distant supernovae. It is responsible for the accelerated expansion of the universe and remains one of the biggest mysteries in cosmology. The detailed observation of galaxy formation and evolution has been made possible by deep-field images from telescopes like Hubble. These images show galaxies at various stages of development, helping us understand how structures form and change over time. The study of black holes, including the first direct image of a black hole by the Event Horizon Telescope, has provided insights into these enigmatic objects. Observations of black hole mergers and accretion disks have deepened our understanding of their properties and behaviors. The detection of fast radio bursts, intensive bursts of radio waves from distant galaxies, has puzzled astronomers. These mysterious signals could help us understand more about the intergalactic medium and cosmic structures. The observation of high-energy cosmic rays and neutrinos provides information about energetic processes in the universe, such as supernovae and active galactic nuclei. These particles travel across vast distances, carrying information about their origins. The measurement of the Hubble constant, which describes the rate of the universe's expansion, has been refined through various methods, including Cepheid variable stars and the cosmic microwave background. However, discrepancies remain, prompting further investigation. Gamma-ray bursts, the most energetic events observed in the universe, provide insights into the deaths of massive stars and the formation of black holes. These bursts are studied using space-based observatories that can detect high-energy radiation. Observations of the large-scale structure of the universe, including the distribution of galaxies and cosmic voids, have helped us understand the role of dark matter and dark energy in shaping the cosmos. Telescopes and satellites play a crucial role in modern astronomy, allowing us to observe and study the universe in ways that were previously unimaginable. Ground-based telescopes, such as those at observatories like Mauna Kea and the Very Large Telescope, provide detailed images and spectra of celestial objects. Space-based telescopes, like the Hubble Space Telescope, have revolutionized our understanding of the universe by providing clear, unobstructed views of space from above Earth's atmosphere. Hubble's deep-field images have revealed countless distant galaxies and provided insights into the early universe. The James Webb Space Telescope, set to launch soon, will further enhance our capabilities by observing in infrared wavelengths, allowing us to see through dust clouds and study the formation of stars and planets in unprecedented detail. Radio telescopes, such as the Arecibo Observatory and the Atacama Large Millimeter Array, detect radio waves from space. These telescopes have helped us study phenomena like pulsars, quasars, and the cosmic microwave background radiation. X-ray telescopes, like the Chandra X-ray Observatory, allow us to observe high-energy events in the universe, such as supernovae, black holes, and neutron stars. These observations provide critical information about the most energetic processes in the cosmos. Gamma-ray telescopes, such as the Fermi Gamma-ray Space Telescope, detect the highest energy radiation from space. These telescopes help us study gamma-ray bursts, active galactic nuclei, and other extreme events. Satellites equipped with various instruments have expanded our ability to study the Sun and its influence on the solar system. Missions like the Solar and Heliospheric Observatory and the Parker Solar Probe provide valuable data on solar activity and its impact on space weather. Planetary missions, such as the Mars rovers and the Voyager probes, have provided detailed information about the planets, moons, and other bodies in our solar system. These missions have expanded our knowledge of planetary geology, atmospheres, and potential for life. The Kepler Space Telescope has been instrumental in discovering thousands of exoplanets by detecting the tiny dips in starlight caused by planets passing in front of their stars. This mission has significantly increased our understanding of the prevalence and diversity of planetary systems. Gravitational wave observatories like LIGO and Virgo have detected ripples in space-time caused by massive cosmic events, such as merging black holes and neutron stars. These observations open a new window for studying the universe. Infrared telescopes, such as the Spitzer Space Telescope, allow us to see the heat emitted by objects in space. These telescopes are crucial for studying star formation, exoplanets, and the interstellar medium. Ultraviolet telescopes, like the Hubble Space Telescope's UV capabilities, help us study the high-energy processes in the universe, including the formation of young stars and the behavior of hot, massive stars. The Gaia satellite is mapping the positions, distances, and motions of over 1 billion stars in our galaxy. This data is helping us understand the structure and evolution of the Milky Way and improve our models of stellar dynamics. Telescopes and satellites also play a vital role in monitoring near-Earth objects, such as asteroids and comets. These observations help us assess potential threats to our planet and develop strategies for planetary defense. Overall, telescopes and satellites are essential tools for modern astronomy. They enable us to explore the universe across the entire electromagnetic spectrum, study celestial phenomena in unprecedented detail, and answer fundamental questions about the nature of the cosmos. Several discoveries support theories of an infinite universe, starting with the observation of the cosmic microwave background radiation. This faint glow, a remnant of the Big Bang, is uniform in all directions, suggesting a vast, possibly infinite universe. Edwin Hubble's discovery that galaxies are moving away from us indicated that the universe is expanding. This expansion implies that the universe could be infinite, continually stretching outwards without end. The theory of cosmic inflation, which proposes a rapid expansion of the universe immediately after the Big Bang, supports the idea of an infinite universe. Inflation could have stretched the universe so much that it appears flat and infinite on observable scales. Observations of the large-scale structure of the universe, including the distribution of galaxies and cosmic voids, show patterns that align with models predicting an infinite universe. These structures suggest a vast and continuously expanding cosmos. The discovery of dark energy, an unknown force driving the accelerated expansion of the universe, further supports the possibility of infinity. If dark energy continues to propel the expansion indefinitely, the universe could expand forever. The multiverse theory, which arises from both inflationary cosmology and string theory, suggests that our universe is just one of many. Each universe in this multiverse could have different physical laws and constants, implying an infinite set of possibilities. Quantum mechanics, with its many worlds interpretation, also supports the concept of infinity. This interpretation suggests that every possible outcome of a quantum event creates a new parallel universe, leading to an infinite number of universes. The observation of gravitational waves has opened new avenues for understanding the universe's structure. These waves, ripples in space-time caused by massive cosmic events, provide insights that could support the theory of an infinite universe. The detailed mapping of the cosmic microwave background by satellites like COBE, WMAP, and Planck has provided data that fits with models predicting an infinite universe. These observations show a universe that is isotropic and homogeneous on large scales. Advances in radio astronomy, such as the discovery of fast radio bursts and their study, contribute to our understanding of the universe's vastness. These mysterious signals hint at processes occurring across immense distances, consistent with an infinite cosmos. The study of black holes and the information paradox challenges our understanding of space and time, potentially supporting the idea of an infinite universe. The holographic principle, which suggests that all the information in the universe can be encoded on a two-dimensional surface, implies a deeper infinite structure. The discovery of exoplanets and the vast diversity of planetary systems suggests that our universe is teeming with possibilities. The sheer number of stars and planets discovered supports the idea of an infinite expanse with countless worlds. Observations of high-energy particles and cosmic rays provide information about processes occurring at vast distances. These particles travel across the universe, suggesting a boundless expanse filled with energetic events. Theoretical work in string theory and loop quantum gravity offers frameworks that naturally incorporate the concept of an infinite universe. These theories attempt to unify general relativity and quantum mechanics, providing insights into the fundamental nature of reality. Ultimately, these discoveries and theoretical advancements support the idea of an infinite universe, challenging our understanding of space, time, and existence. They push the boundaries of what we know and open new possibilities for exploring the cosmos. Technological advancements have revolutionized our ability to explore the universe. The development of powerful telescopes, both ground-based and space-based, has expanded our view far beyond what was once imaginable. Ground-based observatories, equipped with adaptive optics, can now correct for the distortion caused by Earth's atmosphere. This technology allows telescopes to capture sharper images of distant celestial objects. Space telescopes, like the Hubble Space Telescope, have provided unparalleled views of the cosmos. Operating above the atmosphere, these telescopes can observe in ultraviolet, visible and near-infrared wavelengths without interference. The James Webb Space Telescope, set to launch soon, will extend our reach even further. Its advanced infrared capabilities will allow us to peer through dust clouds and study the formation of stars and planets in unprecedented detail. Radio telescopes have also seen significant advancements. Arrays like the Atacama Large Millimeter Array and the upcoming Square Kilometer Array will provide detailed observations of the cold universe, including star formation and molecular clouds. The development of gravitational wave observatories such as LIGO and Virgo has opened a new window for exploration. Detecting ripples in space-time caused by cataclysmic events, these observatories offer insights into phenomena that were previously invisible. Advancements in detector technology have made it possible to observe high-energy phenomena. Instruments like the Fermi Gamma Ray Space Telescope capture gamma rays from extreme events, revealing the universe's most energetic processes. The rise of space missions has also transformed our exploration capabilities. Probes like Voyager, Cassini, and New Horizons have provided detailed data on the outer planets and beyond, expanding our understanding of the solar system. Mars rovers, such as Curiosity and Perseverance, are equipped with sophisticated instruments that analyze the planet's geology and search for signs of past life. These missions pave the way for potential human exploration. The development of reusable rockets by companies like SpaceX has drastically reduced the cost of space travel. This innovation is making space more accessible and enabling more frequent and ambitious missions. Artificial intelligence and machine learning are playing an increasingly important role in space exploration. These technologies help process vast amounts of data, identify patterns, and even control spacecraft autonomously. Satellite technology has advanced significantly, providing critical data for Earth observation and climate monitoring. Satellites track weather patterns, monitor environmental changes, and support disaster response efforts. The International Space Station continues to be a hub for scientific research. Experiments conducted in microgravity provide insights into fundamental physics, biology, and material science that are not possible on Earth. CubeSats and small satellite technology are democratizing space exploration. These affordable, miniaturized satellites allow universities, startups, and smaller countries to conduct space research and missions. The future of space exploration looks even more promising with the development of new propulsion technologies. Concepts like ion propulsion and solar sails could enable faster and more efficient travel to distant destinations. These technological advancements are propelling us into a new era of exploration, expanding our understanding of the universe and our place within it. As we continue to innovate, we will uncover even more secrets of the cosmos and potentially find answers to some of the most profound questions about existence. Future missions and projects are set to push the boundaries of our exploration and understanding of the universe. The James Webb Space Telescope, scheduled to launch soon, will observe the universe in infrared light, studying the formation of stars and galaxies and searching for signs of life on distant exoplanets. The European Space Agency's Gaia mission continues to map the positions and motions of over 1 billion stars, providing unprecedented details about the structure and evolution of our galaxy. NASA's Artemis program aims to return humans to the Moon by 2024, establishing a sustainable presence and using the Moon as a stepping stone for future missions to Mars and beyond. The Mars Sample Return Mission, a collaboration between NASA and ESA, plans to bring Martian soil and rock samples back to Earth for detailed analysis, which could provide insights into the planet's history and potential for life. The Nancy Grace Roman Space Telescope, set to launch later this decade, will survey large areas of the sky to study dark energy, dark matter, and exoplanets, enhancing our understanding of the universe's structure and evolution. China's Chang'e program continues its lunar exploration with plans for more robotic missions and eventually human landings, contributing to our knowledge of the Moon's geology and resources. The Square Kilometre Array, an international radio telescope project, will be the largest and most sensitive radio telescope ever built, aiming to answer fundamental questions about the universe, from the formation of the first stars to the nature of dark matter. The European Space Agency's JUICE mission, set to explore Jupiter's icy moons, will study the moons Ganymede, Callisto, and Europa, looking for signs of subsurface oceans and potential habitability. NASA's Dragonfly mission will send a rotorcraft lander to Saturn's largest moon, Titan, to explore its diverse environments and prebiotic chemistry, offering insights into the conditions that could lead to life. The James Webb Space Telescope's successor, currently in conceptual stages, aims to observe the universe in the far infrared, pushing the boundaries of our observational capabilities and exploring the earliest galaxies and black holes. The Breakthrough Starshot project envisions sending tiny light-powered spacecraft to the nearest star system, Alpha Centauri, at a fraction of the speed of light, potentially providing the first close-up images of another star system. The Vera C. Rubin Observatory will conduct a 10-year survey of the sky, mapping the dynamic universe and providing data on dark matter, dark energy, and the formation of galaxies. SpaceX's Starship, a fully reusable spacecraft, aims to revolutionize space travel by enabling missions to the Moon, Mars, and beyond, with the potential to make interplanetary travel more affordable and accessible. The Lunar Gateway, an international collaboration led by NASA, will serve as a space station in lunar orbit, supporting sustainable lunar exploration and serving as a staging point for missions to Mars. These future missions and projects represent the next frontier in space exploration, promising to expand our knowledge, inspire new generations, and possibly answer some of the most profound questions about our place in the universe. As we look to the stars, the potential for discovery and advancement is boundless, driven by human curiosity and ingenuity. Main scientific challenges in understanding the universe remain numerous and complex. One of the foremost challenges is uncovering the nature of dark matter. Despite constituting about 27% of the universe's mass energy content, dark matter remains invisible and detectable only through its gravitational effects. Similarly, dark energy presents another major challenge. Accounting for roughly 68% of the universe's energy density, dark energy drives the accelerated expansion of the universe. Its true nature remains one of the biggest mysteries in cosmology. The unification of general relativity and quantum mechanics poses a significant challenge. These two foundational theories of physics describe the macroscopic and microscopic realms respectively, but are currently incompatible. A unified theory of quantum gravity is needed to fully understand the universe. Understanding the initial conditions of the Big Bang and what preceded it is another challenge. While the Big Bang theory describes the early universe's rapid expansion, the exact nature of the singularity at the beginning remains unclear. The formation and evolution of galaxies also pose questions. While we have models to explain these processes, the detailed mechanisms of how galaxies, especially those with supermassive black holes at their centers, formed remain to be fully understood. Another challenge lies in the study of exoplanets. While thousands have been discovered, determining their composition, atmospheres, and potential habitability requires advanced techniques and more powerful telescopes. The origin of life in the universe is an enduring mystery. Understanding how life began on Earth and whether similar processes could occur elsewhere is a fundamental scientific challenge. The nature of time and its flow is another complex issue. Understanding why time appears to move in one direction and how it is intertwined with space in the fabric of the universe is essential to understanding the cosmos. Neutrinos, elusive particles with very little mass, pose significant detection challenges. Studying their properties and interactions is crucial for understanding fundamental particle physics and cosmological processes. Exploring the properties of black holes especially those of the elusive intermediate mass black holes, continues to be a challenge. Observing their formation, growth, and the role they play in galactic dynamics remains a key area of research. Gravitational waves, though recently detected, require further study to understand their full implications. More sensitive detectors and extended observation periods are needed to map the universe through gravitational wave astronomy. The cosmic microwave background radiation holds clues to the universe's early conditions, but extracting detailed information from this relic radiation involves significant technical and analytical challenges. Understanding cosmic inflation, the rapid expansion that supposedly occurred fractions of a second after the Big Bang, remains difficult. Identifying definitive evidence and understanding the exact mechanisms behind inflation are critical for cosmology. Investigating high-energy cosmic rays, which are particles traveling through space at nearly the speed of light, involves challenges in detecting their origins and understanding the processes that accelerate them to such high energies. Finally, exploring the concept of multiverses and higher dimensions, which some theories suggest, remains speculative without direct evidence. Developing ways to test these ideas experimentally or observationally poses one of the most profound challenges in modern physics. These challenges drive scientific inquiry, pushing the boundaries of our knowledge and capabilities. As we develop new technologies and methodologies, we move closer to answering these fundamental questions about the universe. Prominent debates in cosmology continue to shape our understanding of the universe. One major debate revolves around the nature of dark matter. While it is widely accepted that dark matter exists, its composition remains unknown, with candidates ranging from weakly interacting massive particles to axions. Another significant debate concerns dark energy. This mysterious force driving the accelerated expansion of the universe remains poorly understood. Scientists debate whether it is a cosmological constant, as Einstein proposed, or a dynamic field that changes over time. The origins of the universe present another area of contention. The Big Bang theory is the leading explanation, but what triggered the Big Bang and what, if anything, preceded it remain hotly debated topics. The nature of black holes is also a subject of intense discussion. While their existence is well established, questions about what happens inside black holes, particularly regarding the information paradox and singularities, continue to challenge our understanding. The multiverse theory generates substantial debate. Proponents argue that multiple universes could explain the fine-tuning of our own universe's constants, while critics point to the lack of empirical evidence and testability as significant drawbacks. The interpretation of quantum mechanics fuels another debate. The many-worlds interpretation suggests every possible outcome of a quantum event occurs in a separate universe, while the Copenhagen interpretation holds that outcomes depend on the observer's measurement. The true shape and extent of the universe are debated as well. While the observable universe appears flat and infinite, the overall topology of the universe could be finite but unbounded, or it could be one of many possible shapes. Inflation theory, which posits a rapid expansion of the universe immediately following the Big Bang, is widely supported but still debated. Some scientists propose alternative theories like ekpyrotic or cyclic models that challenge traditional inflationary scenarios. The ultimate fate of the universe is another contentious issue. Depending on the properties of dark energy and the overall curvature of the universe, it could expand forever, collapse in a big crunch, or reach a stable size in a big freeze. The nature of time and whether it is fundamental or emergent from deeper principles remains a major debate. Some theories suggest time may not be a fundamental aspect of reality, but a result of entropic processes. The fine-tuning problem, where the constants of nature appear to be precisely adjusted to allow for life, raises debates about whether this is due to a multiverse, intelligent design, or some unknown principle of physics. The role of observational cosmology versus theoretical cosmology continues to be discussed. While observations provide critical data, some argue that theoretical frameworks often outpace our ability to test them empirically. The concept of space-time and its structure at the smaller scales is another area of debate. Theories like string theory and loop quantum gravity offer different visions of space-time's fundamental nature, each with its own implications and challenges. The question of whether the universe has a purpose or is a random occurrence is a philosophical debate that intersects with cosmology. This debate touches on the broader implications of scientific discoveries for our understanding of existence. These debates drive the field of cosmology, fostering critical examination and innovative thinking. As new observations and theories emerge, they will continue to shape our understanding of the universe and our place within it. Criticisms of current theories in cosmology highlight several unresolved issues and areas of contention. One major criticism is that dark matter has not been directly detected. While its gravitational effects are evident, the lack of direct evidence for dark matter particles leaves room for skepticism. Dark energy, which accounts for about 68% of the universe's energy density, is another contentious point. Critics argue that it is a placeholder for our ignorance, and its true nature remains speculative and poorly understood. The Big Bang theory, though widely accepted, faces questions about the initial singularity. Critics argue that a singularity represents a breakdown of physical laws, suggesting that our current understanding is incomplete. The theory of inflation, while addressing several problems of the Big Bang theory, such as the horizon and flatness problems, is criticized for its lack of direct evidence. Some argue that the parameters of inflationary models can be fine-tuned to fit any observational data. String theory, which seeks to unify general relativity and quantum mechanics, is often criticized for its lack of testable predictions. Critics argue that it remains more of a mathematical framework than a physical theory with empirical support. The multiverse theory faces significant criticism for its untestability. While it can potentially explain the fine-tuning of physical constants, the inability to observe or interact with other universes makes it a highly speculative concept. Quantum mechanics, despite its successes, is criticized for its interpretations. The Copenhagen interpretation, which involves wave function collapse, is seen by some as incomplete or unsatisfactory, leading to alternative interpretations that are equally contentious. Loop quantum gravity, an alternative to string theory, is also under scrutiny. While it aims to quantize spacetime, its predictions are challenging to test, and it has yet to produce a definitive unification of general relativity and quantum mechanics. The standard model of particle physics, while successful in many respects, does not incorporate gravity and has limitations in explaining certain phenomena, such as the masses of neutrinos and the nature of dark matter and dark energy. Critics of current cosmological models also point to the fine-tuning problem. The precise values of physical constants required for the existence of life seem unlikely to be a result of chance, leading some to question whether our models are missing a deeper principle. The anthropic principle, which is often used to explain fine-tuning, is criticized for being unscientific. It suggests that the universe must allow for the observer's existence, but does not provide a mechanism or predictive power. The reliance on the cosmological constant to explain dark energy is also debated. Some argue that its value appears unnaturally small, prompting theories like quintessence. But these alternatives also face challenges in gaining empirical support. The nature of singularities in black holes is another area of criticism. The concept of a singularity, where densities become infinite, suggests that our understanding of gravity breaks down under extreme conditions. The interpretation of cosmic microwave background data is sometimes questioned. While it provides critical evidence for the Big Bang theory, the exact nature of its fluctuations and their implications for cosmological models are still debated. Ultimately, these criticisms highlight the dynamic and evolving nature of cosmology. As we develop new technologies and gather more data, our theories will continue to be tested, refined, and challenged, driving the progress of our understanding of the universe. The future of research in cosmology promises exciting developments and profound discoveries. Advances in technology will play a crucial role, enabling us to explore the universe in greater detail and across a broader range of wavelengths. Next-generation telescopes, both ground-based and space-based, will provide unprecedented resolution and sensitivity. Instruments like the James Webb Space Telescope and the Extremely Large Telescope will offer new insights into the early universe, star formation, and exoplanetary atmospheres. Gravitational wave astronomy is expected to expand significantly. Improved detectors and new observatories, such as LISA, will allow us to observe more events and probe deeper into the universe's history, including the moments just after the Big Bang. Research into dark matter will continue to be a major focus. Experiments designed to directly detect dark matter particles, such as those at underground laboratories and colliders, aim to uncover the nature of this elusive substance. Dark energy research will also intensify. Projects like the Dark Energy Survey and the upcoming Euclid mission will help us understand the force driving the universe's accelerated expansion and its implications for the cosmos. The study of black holes will advance with better observational techniques and theoretical models. The Event Horizon Telescope's future observations will provide more detailed images and data, enhancing our understanding of these mysterious objects. Exoplanet research will continue to grow, with missions like TESS, CHEOPS, and the James Webb Space Telescope, searching for potentially habitable planets and analyzing their atmospheres for signs of life. Quantum-cosmology will explore the intersection of quantum mechanics and general relativity. Theories such as loop quantum gravity and string theory will be tested and refined, seeking a unified description of the universe's fundamental forces. AI and machine learning will become increasingly important in analyzing vast amounts of astronomical data. These technologies will help identify patterns, make predictions, and optimize observations, accelerating discoveries. The study of the cosmic microwave background will remain a key area of research. Future missions will aim to measure its polarization and temperature fluctuations with greater precision, providing deeper insights into the universe's infancy. The potential discovery of primordial gravitational waves will be a breakthrough, offering direct evidence of inflation and providing a window into the universe's earliest moments. The development of new propulsion technologies will expand our ability to explore the solar system and beyond. Concepts like ion propulsion, nuclear thermal propulsion, and solar sails could enable faster and more efficient space travel. International collaboration will be crucial for the future of cosmology. Large-scale projects and missions will increasingly rely on cooperation between space agencies, universities, and private companies to pool resources and expertise. Citizen science initiatives will continue to engage the public in astronomical research. Projects like Galaxy Zoo and Planet Hunters harness the power of crowdsourcing to analyze data and make discoveries, fostering a broader interest in science. As our understanding of the universe grows, philosophical and ethical considerations will become more prominent. Questions about the implications of our discoveries, the search for extraterrestrial life, and the use of space resources will require thoughtful reflection and dialogue. The future of cosmology is bright, with new technologies and collaborative efforts paving the way for groundbreaking discoveries. As we explore the universe's mysteries, we will deepen our understanding of the cosmos and our place within it, continually expanding the frontiers of human knowledge. In this video, we've explored the profound and fascinating concept of an infinite universe, delving into its implications, scientific foundations, and the ongoing debates surrounding it. We began by examining what it means for the universe to be infinite, considering both the philosophical and mathematical definitions that challenge our understanding of space and time. We discussed the philosophical implications of an infinite universe, highlighting how different cultures and thinkers have grappled with the idea of infinity. From ancient Greek philosophers to modern scientific thinkers, the concept of infinity has always inspired deep reflection and debate. Our journey continued with a look at the evidence supporting the Big Bang theory and the role of dark matter and dark energy in shaping our universe. These mysterious components make up the vast majority of the cosmos and are crucial to understanding its expansion and ultimate fate. We also explored alternative theories to the Big Bang, such as the multiverse and cyclic models, which offer different perspectives on the origins and nature of the universe. These theories push the boundaries of our imagination and scientific inquiry, suggesting that our universe may be just one of many. The role of quantum mechanics and its implications for our understanding of the cosmos was another key topic. Concepts like quantum entanglement and superposition challenge classical notions of reality and open new avenues for exploring the fundamental nature of the universe. We discussed the importance of technological advancements in space exploration, from powerful telescopes and satellites to groundbreaking missions that expand our knowledge of the solar system and beyond. These technologies are essential for testing our theories and making new discoveries. Prominent debates in cosmology, such as the nature of dark matter, dark energy, and the true shape of the universe, highlight the dynamic and evolving nature of this field. These debates drive scientific progress and inspire innovative thinking as we seek to understand the cosmos. We also examined criticisms of current theories, acknowledging the unresolved issues and areas of contention that continue to challenge scientists. These criticisms are crucial for refining our models and pushing the boundaries of our knowledge. Looking ahead, the future of research in cosmology promises exciting developments. Next-generation telescopes, advancements in gravitational wave astronomy, and new space missions will continue to expand our understanding of the universe. International collaboration and citizen science initiatives will play a vital role in these endeavors. Finally, we reflected on the intersection of science and philosophy, emphasizing how both disciplines contribute to our quest to understand the infinite universe. As we continue to explore the cosmos, we will deepen our appreciation of the mysteries that surround us and the remarkable journey of discovery that lies ahead. If you enjoyed this video, please like and subscribe to our channel. Be sure to check out the rest of our videos for more fascinating insights into the wonders of the universe. Thank you for watching, and we'll see you in the next video.